Okay, welcome to fifth day of second week of ST4 2020. Today, first we have lectures on complexity. It will be shared half by Pratik Nandy and half by Aranya Bhattacharya. First, Pratik will go. Over to you, Pratik.
Okay, so today we will discuss about what we have left yesterday. So we have seen the Louisville action as given the complexity as given in terms of the Louisville action in the path integral approach. So today, what we first we discuss what is the role of the penalty factor. So without the penalty factor, we discussed the Louisville action without the penalty factor yesterday. So now we introduce the penalty factor in the derivative direction. This derivative terms. So this is the potential term and this is the kinetic term, which is the derivative term. So uh, according to the Nielsen, you can penalize a direction which seems a hard direction or multi-qubit gates. So we penalize this direction, this derivative direction. So the role of this penalty factor is to give a high cost in this direction. That means when the penalty factor is higher, the cost of this direction is higher. That means this kinetic term gets somehow decoupled from this potential term. So in this language, we can think this penalty factor as some sort of coupling between these two terms. But still now we didn't have any form of how it looks like. But it suggests that the coupling has some inverse relation of this penalty factor. When this penalty factor is high, these two terms get decoupled, and the penalty factor, this coupling becomes a low. So some kind of inverse relation. So we'll get to see what kind of coupling we can give attribute to this penalty factor. So as before, this Louisville action is just into this penalty factor where the z is the Euclidean time and this and x is the directions. So now we extremize this Louisville action to get the equation of motion, and the solution is just with the penalty factor here. Then the boundary condition is at z equal to epsilon, just we have seen yesterday, is p square by epsilon square. Now on this solution, we want to evaluate the complexity. So on this solution, we do the z integration first, and we get a term like 2p square by epsilon square. Now, as before, we have said this Louisville action can be termed as a total number of gates. So in the total number of gates is depends on this epsilon. In this language, we can think this epsilon as a error tolerance that we previously what Aranya previously discussed when it discussed about Nielsen paper. So this epsilon is kind of tolerance. So SL is the total number of gates. So we want to extremize this total number of gates with respect to tolerance, because in some experimental setting, we don't want that our total number of gates should grow with the tolerance, should go to infinity actually. So we want to extremize this, minimize this total number of gates with respect to tolerance. So we get this condition, and this can be easily solved as the p is square root of epsilon. Now we define this. If we define this, g is a 1 over log of p and epsilon is 1 over lambda, then we can get similar like a kind of like a beta function equation we see in the quantum field theory. So we call this the flow function, and this is a positive flow because it's a positive sign, and this flow function has some interpretation in when we discretize this when you consider the discretized version of this of the complexity. So it suggests that bulk is harder where the boundary is easier, but currently in this language we don't see this. So in the bulk boundary representation, I will not talk about this thing, but this flow function has a precise interpretation when in terms of discrete complexity. So on this solution, we calculate the Lagrangian density, which is given by this 2p square by z square term with the factor c by 24 pi. So this is a c by 12 pi p square epsilon square, and on the estimation condition, this is just a 1 over epsilon term. and one can see this at, evaluated at z equal to epsilon. This is the monotonic function of in epsilon, this L holographic in estimation condition. So is suggests this kind of is a boundary C function which is a kind of monotonic function of C, but we have to relate this in terms of RG flow to connect this. So it suggests that L hologram estimation is a total is a number of local quantum gates per unit space-time volume. So is we can consider this holographic estimation is a identify the density of gates, because this S is a total number of gates. So this similarly can be termed as a density of gates. So there is a 1 over C over 24 pi should be there factor.
Pratik, can you turn on your camera?
Turn, okay. Sorry. Yes. Okay. So we have to find this. What is the holographic or especially the RG interpretation of this density of gates that we have identified. So to identify this, we write a d-dimensional metric for the RG flow metric in QFT is given by this very well-known form. This is 2 epsilon square. This is the boundary term. This is the bulk term. So at the fixed point, this is the proportion. This function is proportional to R. So we get in 2 dimension. We get something like we get a form like this. This is because this is the ADS metric. When you form 1 over Z, R is equal to 1 over Z, it becomes an ADS metric. So one can easily get the H2 slicing by defining e to the power 2 r by 1 over Z square. So this is just there's a H2 slicing in the boundary. So on the fixed point, on the solution that we have shown is given by 1 over Z square. So one can identify this e to the power 2a is just a 1 over epsilon square. It's without the penalty factor for now. So we propose that the same identification can be done even after introducing the penalty factor. So our form is t to the power 2a is just a p square by epsilon square, and this suggests that there is trivial rescaling of the cutoff epsilon by epsilon over p. So we have to interpret what this means actually in terms of the density of gates. So we'll come back later. So there is a famous result for the monotonicity of this function AR, which is defined in this form, and in 2 dimension this AR is a AR, both the small AR and capital AR as a monotonic function that can be seen as the matter set to satisfy the null energy condition. So given this equation, you put the Einstein equation, and you can see this function AR satisfies the average null energy condition. So this is just a monotonic function AR. So our identification is follows from this. Just exponential 2a is a factor of p square by epsilon square, which is proportional to this holographic that you have suggested. So this holographic evaluated on this external extremation condition is just a C function, and is geometrically, and this monotonicity of AR is geometrically related to the monotonicity of this holographic estimation on the fixed point. On the fixed point. So as you have said, this we have to term this what this means actually. This rescaling. So you see, this rescaling is just if we rescale this, we give a higher cost. That means if we increase the penalty factor, this epsilon get decreased. So epsilon decrease means when you do the path integral approach, you get close to the 0 point. So that means that you are decreasing your error. That means your number of gates has to be increased. That is precisely what what is the density of gates suggested. That this holographic is when you decrease the epsilon, this holographic density of gate increases. So this is a consistent with the condition that if you go beyond some if you decrease your tolerance, you have to increase a higher number of gates, and in some point it has to be breakdown that you cannot increase your number of gates. So that is something you have to precisely put a cutoff where you up to some value when give some tolerance to your theory. So this is the interpretation of this density of gates in terms of RG flow. So So now I just made a quick summary. Maybe I have finished quicker. So quickly, so this is just a higher dimensional. The question is that where can we find a higher dimensional version of this Louisville action? So Check suggested that there is some higher dimensional version in the, if you argue from tensor network language. So this is just a volume contribution, and this is just a surface contribution that we have yesterday discussed. And this d minus 2 factor is just because you are doing your tensor network in 2 dimensions, and the other d minus 2 dimensions are just give volume contribution. So this is d minus 2, but there is a problem with this because they can have some subleading term also, because that higher dimensional version of the Mera is not developed. So this is just an approximate thing that the leading contribution has to be like this. So in this paper, the people of this Max Planck group suggested that Liouville function can be described in terms of a cost function. So this is just a cost functional. So if you expand these terms in terms of derivative expansion of the A and B, then the first two terms is precisely the Liouville action, and there are subleading terms. So the question is, in what condition you can ignore the subleading terms and give precise the Liouville action. So the condition is not yet known. So this is kind of approximate thing that we are trying to do, but is not known. So the question is, the higher dimensional version of the Liouville action is precisely from the first principle derivation is still unknown, and people are just working on it to get the from a pure gravity side, from this whatever we did from the pure CFT side. So the result from the pure gravity side, from the, for example, the ball contribution from the given sucking term and the counter term contributing everything, the current principle of first principle derivation that we did is currently not known. So this is just a progression that people are doing. So this is what I have to say. So thank you.
Okay. So we have plenty of time for the questions and discussions on Pratik's part. So if anyone has any question or want any clarification, want to ask any question, this is a good time to go ahead.
Pratik,
Yes.
so since we have time, so just go back one slide from here. When you first introduce the penalty factor or function, said something.
Yes.
Right. So this p square epsilon is a penalty factor, right? And then when you write the higher derivative term, the last action that you have shown, so there was e to the power d minus 2 phi factor, right? So is that your penalty function now? If you are d minus
no. For example, if you consider in 3 dimension, it is just e to the power phi del phi square del x plus del z square plus just this potential term. So this is not your penalty, because in a whatever penalty factor we are introduced is in 2 dimension. It's not in 3 dimension.
right, but it looks the okay. 2 means then that function, that action does not boils down to this 0.66 equation. And this
no, even for example, if you have a 3-dimensional version of Liouville equation exactly looks like this, then you have to introduce a penalty factor again in terms of the kinetic, in terms of this kinetic term. So because in the 2D in 3 dimension you have also an exponential phi term here. So here
you have to introduce this p square term there by hand.
By hand, yes. The very first principle in Nielsen is that you have to introduce the penalty factor by hand, which gates you are going to give a high cost function. There is no fundamental principle, or by some rescaling or some trivial coordinate transformation you cannot introduce this penalty factor. So whatever penalty factor, you do it by hand. Yes.
So now that this p square epsilon was your related to a boundary on e to the power 2 pi, right? The
Yes.
Just
Yes.
go to the next slide. So p square epsilon was, yeah, exactly. So this is the boundary relation, right?
Yes.
So now, so when you introduce in the higher derivative case also, that whatever cost function you are introducing, like it have to be p square epsilon, or But
No, this
or the solution will turn out to be something different.
something different, yes, because they have an exponential 3 phi and exponential 5, for example,
Okay.
3 dimensions. So there are some different solution.
Right. Also, there is no fundamental.
No. But the very construction of the Nielsen, so what the people are trying, the Nielsen introduced this penalty factor by hand. So
what I thought was just 0.67. The last slide, you have this equation of motion, right? Sorry.
it's
So
just
not the last slide. I mean, the first when you introduce penalty factor, that slide. 0.67 equation. Yes. So here I thought that this is the primary thing, and 0.66 is the action which will give you 0.67. That's what I was initially thought. So in the higher derivative case, that's why I was thinking that probably that's whatever in front of this del z pi del I pi square. That
another
should be
term,
right.
another term.
Okay. Okay.
So the Nielsen, so the one thing I should mention that the Nielsen, this penalty factor is you are putting by hand and you are free to choose by hand, whatever high value you can do. But here the thing is that you cannot put by, I mean its value cannot be arbitrarily chosen. So there is a difference between what Nielsen's and what ours, because this is just a function of epsilon. So the epsilon is determined from the solution and other things in the equations. So in the very construction of Nielsen, you can penalty for the qubit case, you can penalize the gates, for example, in a 4 to the power n or something like this, so that you can go to a you can restrict yourself within some boundary. But here is not. So here PA determines with the epsilon itself. So there is a flow of penalty factor. That's what we call the flow function. If this penalty factor is just a constant, you can do it by hand. So there is no flow function and there is no RG things like this. So so another thing I would like to mention, this in the case where in the previous day we said is there is some which is introduced some epsilon in the path integral thing. So the connection is that what is the role of this epsilon. So the epsilon is the epsilon that we have done in the path integral is basically exactly the tolerance, and this is exactly the same interpretation in terms of the gates that Aranya was the first day discussed, that we have some tolerance between the gates, but this is some field theoretic language. So this is just a lattice spacing or some in the limit in the cutoff in the path integral, or is the just tolerance in this language. So both are exactly the same. So these things are just connected. So in this various construction. So yes, just like this. Yes.
Pratik, can you just briefly comment or describe what are the pressing open questions in this program, and what are some of the future directions? Like what are people thinking?
Okay, so this is so in this tensor networks and things are in this tensor network, and the path integral kind of optimization is one, just the last slide I mentioned. Is that tensor networks are well developed in 2D cases. For example, simulating the 1 dimensional ground states. But is the current formulation of the tensor networks in higher dimension is not known. So that's why we can argue that this is kind of a reveal equation in 3D or higher dimension can look like, but this is not the precisely what actually can be. There can be a subletting terms. Because there is no fundamental principles to derive tensor network principles from higher dimensions. So there is a one way to see how can derive the tensor networks from in higher dimension, and what can be the Liouville equation from that argument. Another thing is that the Liouville equation is the first principle derivation that I've said. The derivation of the Liouville equation consistent with gravity is still missing. So people have argued from this anomaly approach or this tensor network approach, but this is not from this is purely from the field theory side. There is no calculation that we can go from and see this in the Liouville in the gravity side. It's a Liouville equation. So and in higher dimension, this Liouville action is can be written in terms of some Q curvature action also. Some people are trying also. So at least, I mean, we are trying that thing. So this can be a good direction to. So if there's some compact form of the Liouville action, and how this connects with the anomalies. For example, in four dimension, there are Euler anomalies and Euler anomalies. So how they are connected in this language. So in the field theory side. So that can be a feature direction as well. So
okay, can you just briefly say it again? That what do you mean by first principle derivation? Like what do you have in mind?
So first principle derivation means, so here we have derived the Liouville action in terms of the field theoretic language, right? So first principle means we start from a bulk action, means that there is an Einstein-Hilbert action, there is a Gibbon shifting term, and there is a counter term we have to consider.
I see.
So is there a way that we can get from this three equation this Liouville equation? So if this is true, if we get a Liouville equation in 2D, so this basic principle also give us the prescription how to do that in the higher dimension. Because when I derive the Liouville equation, for example, in the very first slide, so this factor, this is very valid for in 2 dimension, because anomalies in 2 dimension you can always write in e to the power 2 5, but in higher dimension you cannot write this thing. So for the higher dimension, these things is just invalid. So there should be some fundamental principles which can be calculated this complexity in some fundamental way. Not just, this is a kind of special case in 2 dimensions, but it's not true in higher dimensions.
Okay. Any other questions, comments?
I think probably you just said it, but anyway, just go back to the first equation when you have this penalty factor thing. So in Liouville action, normally for curved, you normally you have root G and G mu nu in front, right? For Liouville action in some curved system. So P square, can you take it as root G, or have you talked about it? And P square epsilon, you can you imagine 0.6 this equation as in some curved space time, and this P square is actually kind of the root G factor in some sense.
Yes,
If you look at a generic Liouville equation, the Liouville action does looks like this, right?
Yeah.
Tell me phi.
So we have started from a flat metric, just a 1 by epsilon square, right? 1 by epsilon square dz square plus dx square. So if you start from a P square by epsilon square, so
right.
this gives like this. So you can think this is kind of root G factor, but in 2 dimension, this flat metric is always this. This you can write everything in the conformal factor in flat metric, right?
That's true. Yes.
So
okay.
I think this 2 dimension is a kind of a trivial thing. Yeah, for 3 dimensions, I think this is a non-trivial, because there's some epsilon to the power 5 factor will be there. So then some G change.
Okay, so what you are saying is that it's not a good right way to think of this P square E of some density. I mean, some root G or something, not like that.
Yeah, because one thing that we have introduced this by hand is not something that is inbuilt.
Yeah, that's why I was thinking that when you are introducing it by hand, probably you are going to some kind of curved space time or something. I don't know. I'm just thinking and just thinking out loud in some sense. I was thinking that P square epsilon, can you just take it as some root G?
Maybe because when we discuss this, tensor picture, we said that instead of doing the path integral in flat space time, we have to do path integral in H2 slice.
Right.
To get the optimal solution.
Right.
So
exactly.
so there is some connect.
Yes. Right. That's one way I was thinking, that probably your P square epsilon is the measure. I mean, in some sense, it's telling you like what should be your, like, in that sense, if you took H2 in that case, probably here something different or whatever come from. Let's see.
If you interpret the P square as square root G factor, shouldn't that be in sort of competition with the e to the power 25.
Yeah, that's true. But e to the power 25 will have some, normally in Liouville action, you have this extra parameter, right? Some lambda or something.
Yeah, something sits before it.
Sits in front the e to the power 25. So
I mean, original Liouville, you also have, like in a curved background, original Liouville also has a background charge, right? So it has
exactly.
a Ricci scalar times phi type of factor.
Right.
For example.
So that also something like that has to come, right? Yeah. That RG phi kind of factor.
Right. That's why I was thinking that probably something.
I think Karan has a comment or question. Karan?
Sure.
Yeah, I was just curious if there is any kind of connection between the way you've done this setup in 2D with a Rindler setup. Is this connection known? Because if it was known, then you could generalize that to higher dimensions quite easily. Then you'll always have this nice property of the 2D to go along, and you'd ignore the other directions.
No, I don't know that. I've not seen anywhere. We have to think. I have not seen anywhere this connection. For example, in the case of the.
Has there been any kind of proposal for complexities for field theories with gauge bosons or fermions?
No. Currently, no. There is a complexity. There is a paper in E1 gauge theory on people. Few people have did 1 or 2 papers, but.
So just U1 gauge theory, or is there some charge matter?
No, just E1 gauge theory in the
free Maxwell field.
Yes. In the lattice setup, but I have not gone through the paper. But this construction is different. I mean, this not this path integral approach. This is something in the gate approach that Aranya talked about.
And what about fermions? So, for example,
yes, fermions. There are even Meyer himself did this fermion for example, the free fermions cases.
And what about some kind of U-power interaction between fermions and scalars?
So the complexity for 5 to the power 4, for example, if you interact at a 5 to the power 4 interaction, so this analysis, I mean, Anindo did it in the previously after the Myers did, but for example, in the interaction with fermions, there is no paper as such. I mean, there is no paper which can talk about the interactions actually, except what in the 5 to the power case for Anindo did. Otherwise, there is no interactive interaction case.
Can you briefly comment, like, what is the difficulty, what is the obstruction?
Okay, so in the introduction in the free theory case, so you have to choose a final state, right? You have to choose a target state and a reference state and a target state. But if you go to the interaction theory, there is the target state. Choosing the target state becomes very complicated. So the internals that's the sense. I mean, if you have a Yukawa theory, so what kind of target state you are aiming for? That's the question. So if you have a 5 to the power 4 theory, you can perturbatively construct a target state. But in general, this is a difficult question, and that also includes how your gates should be. For example, in free theory, your gates are just x and p in terms of x and p. So when you consider go to the 5 to the 4 theory, for example, in perturbation theory, your gate should also have this perturbation parameter, and that becomes very difficult and very approximate things. It's not very well defined thing in that sense.
I see. Any other questions, comments? I mean, some people joined a bit late. To them, let me tell you that Pratik has already finished his presentation that he meant to do today. So, I mean, if you have any questions or comments to ask specifically to Pratik's part, it's a good time to ask now, because after this, Aranya will take the rest of the time to finish certain things that he didn't get to finish.
Yeah, I have something, but I mean, I'll say it, but you can also reply it later. I don't know. That since you talked about Mera and Simira, so last week or the previous week before that, there was a paper by Swingle and group about with the title "Conformal Field Theories Are Magical." So, so where they say they talk about the preparation of ground state and how using T gates is a non-Clifford operation, and then to do that, they use some degree of measure of its non-Cliffordness, something called as a mana, and then they use Mera techniques there. So for me, I mean, I was just curious to see that what they're doing and using Mera and all. And also, since it came so recently, are there any new directions there? If you are aware of that paper?
No. So what were you said?
It's a paper by Swingle and more people. The title is "Conformal Field Theories Are Magical." So where they say that this magic is the degree of non-Cliffordness of the gates that they use, and difficulty in using T-gate to prepare a ground state, and then they use some Mera techniques there. So I don't know more. I was just wondering if you know, and if
No,
there
no,
are
I'm not familiar.
directions there.
I can look into that paper.
Yeah, okay, yeah, sure, thanks. Then yeah, we can discuss it later.
And Lata, you can post the paper in Slack maybe, so I think others will
Yeah,
also get it.
yeah, I'll do that. I'll do that. Yeah, for me, it was interesting to see that there are these connections between conformal field theory and ground state preparations, and then Mera. So it all looks very, very new. All of this. So yeah, I'll post it.
Yeah, sure, thanks. Yeah, Karan, go ahead.
Yeah, regarding the gauge theory thing, I wonder if QED3 is sort of tractable in this setup, because QED3 sort of has certain nice conformal properties, and I think there you can define well-defined target states. So I think it might be possible again. But has anybody looked at that? The case of QED3?
No.
Okay.
So another problem is that when you define your target state, you choose your Hamiltonian, right? But this Hamiltonian, what is the state of this Hamiltonian? But in the QED and other this gauge
No, I'm talking about QED in 3 dimensions.
QED in 3 dimension. No, current
So
because
it has certain quote unquote nice properties.
okay.
So you can
Okay.
Yeah, I think it might be possible because QED3, the gauge boson, you can dualize it to a scalar essentially, right?
Exactly.
So
Yeah.
it might be possible in 3 dimensions. Especially since, as Pratik said, that even for free Maxwell, somebody has already done it. So, by the way, free Maxwell for how many dimensions, Pratik? The paper that you mentioned.
I think it's in 4 dimension. You want gauge in 4 dimension.
I see.
I just forgot. I have to check that paper. I can post that paper also.
Yeah, sure. So, any further questions, comments for Pratik?
So as I've said, this definition of the complexity in the field theory language is still unknown. What is the correct? I mean, what should be the definition of complexity? So this field is still missing the main question. Okay, if someone asks what is the definition of the complexity in the field theory language, so the answer is no, we don't know actually. So there is lots of things has to be done even in the field theory language. That's it.
Sorry, one final question. Did you get to the part where there is some, if not a proof, a direction towards the proof of a minimal number of gates needed in the setup? I mean, coming from the Louisville actions. If you're just looking at the Louisville action or any Louisville-like action, that there's a well-defined notion of complexity, at least in terms of some maximization procedure. I mean, something which will be perhaps intrinsic to all theories. Is there any such thing? To come specifically to your 0.66, does p square give you this information in any way? Like, is there some bound on the cost function that you have, this penalty factor?
No, as such is no. In principle, when you evaluate these actions without the penalty factor, for example, this action is always as an infinite because you have a divergence. So, in principle, your theory contains a infinite number of gates. So, if you want to simulate a state exactly, so there need an infinite number of gates. But the point is that in experimental setup, for example, if you think want to prepare some state, you need a finite set of number of gates. For example, if you go some optics lab, you can build the gates in terms of beam splitter, in interferometer, and something like that. So if you suppose in experimental setup, some experimentalist tells you that, okay, I have this number of these gates, and I can prepare the state within this tolerance. So you can give you can see this in theory. You can calculate and give him some interpretation that, okay, our theory looks like this. So suppose if she gives some different tolerance, then theory becomes different. Your total number of gates will again change. But in the experimental setup, you don't want to change your gates, your total number of gates. You always want to fix your gates and do whatever things. So there lies this penalty factor. So this penalty factor is basically, in the Nielsen language, is just a geodesic distance. This penalty factor. So there is something in theoretically you have to control, something that you can control and change according to the error, that estimation that the experimental setup experimentalist can give you. So in this language, your total number of gates is still infinity or something infinity, but by this estimation condition, for example, your gate is some n, capital N is a huge number, but you are fixing this gates, as gates is not increasing if you reduce the tolerance. So the total number of gates is still a kind of infinity, even you whatever you introduce the penalty factors or no, is.
Okay, so just a short follow-up on that. So you're saying p square is linked to this Nielsen notion of geodesic distance, but we also know that this Nielsen notion of geodesic distance depends on the group manifold that you began with. Yes. So are you saying something like the way in which you proceed about complexity depends on what you call hard and what you call light? Is that what you're saying? And that is arbitrary? So, like I can choose something to be hard and then I can change, like whatever I'm calling as the dense part of the Hilbert space, it depends on that definition. Is that what you're saying?
Yes, for example, in Nielsen, they penalize the more than 2 qubit gates, because more than 2 qubit gates are experimentally hard to build. So they penalize the more than 2 qubit gates. So here we penalize the derivative direction. So in the kinetic terms, we see this kinetic derivative terms are principally hard to go in the geodesic manifold. There are derivative directions, so they are hard to in the rigid direction. So we can penalize this direction. So we see this. We'll choose a high cost for this penalized direction instead of this potential term. So in even in the manifold, you think this is some direction and this is also some direction, and we are penalizing this is hard direction, like the Nielsen did for the two. So these are analogous of this multi-qubit gates, and these are the analogous of the single qubit gates. Just analogy, it's not a precise connection. Is that your questions?
Yeah, I'm good.
Okay, I think let us all thank Pratik by unmuting ourselves and clapping for his not only today's lecture but the entire series. So Aranya, if you are there, can you switch on your screen share? And Pratik, you can turn off your screen share.
Yeah.
Was
Hello.
Yeah, hi Aranya. We can see your iPad screen.
Yeah.
Do you want to turn on your video?
Let me.
Okay, the second half of morning session will be taken by Aranya. He will continue telling us about CFT aspects of complexity. Over to you, Aranya.
Yeah. So thank you. Before beginning to talk about the CFT aspects, I'll actually make some comments about what I did previously. So we learned how to compute circuit complexity for free field theories, for free bosonic field theories to be precise, and also for how to do it for pure states and for mixed states. And for mixed states, we did it by something called complexity of purification. So there are also parallel method of doing the same thing, that is computing the circuit complexity, but instead of, for example, previously we uh, marked the space of states by 2 cross 2, for example, for two oscillators, by 2 cross 2 real matrices. For n oscillators, it would just be n cross n real symmetric matrices, by which we mark the our space of states. But instead of the real entries there, had we taken up a scenario where the entries might be imaginary in general. For example, there are a few situations, one example of which should be a particular quench solution, firstly studied by Kaputa and Sumit Das and collaborators, in which they found that the they studied a time-dependent quench, and the wave function had, for a particular time dependence of the frequency, the wave function had an exact solution. And but in that case, the matrices that we dealt to mark the space of states, there we would have imaginary entries. And for that, one typically takes something, instead of the GL2R or GLNR group, one takes the SP2NR or SP2R group, that is the symplectic group, and there one chooses the gates, and that problem is dealt by handling something called covariance matrix, which, for example, we told earlier that we would only deal with Gaussian pure states. When we talked about complexity of purification, we reached a Gaussian purified state from a mixed state. So for a Gaussian, as we know, or second moments know most about the theory. Up to second moments, if we can know everything. So these second moments are 2-point correlators of position and momentums, or expectation values of positions and momentums. They form a matrix called covariance matrix, and in the language of covariance matrix, the study of SP2NR or symplectic case becomes easier. And one has also shown results that people have shown that this choosing GLNR and SP2NR can be related to each other when you really get from the imaginary entries to real entries. And also for more general situations, they have some, but even if you get to real entries, there would be some differences between them. So that is not yet very much clear that how to completely match those two things with each other. But nevertheless, using those techniques, one has studied that for the particular quench solution that I mentioned was studied by Sumit Das and Kaputa, people took that solution and showed that using the covariance matrix approach, one could study complexity, and by the plot of complexity near the critical point of time where the quench happens, one can find signatures of quench in the complexity plot as well. So, but I'll not be talking about those stuff today. I just wanted to mention this study as a parallel one, and I will maybe put a few references in the Slack about this. So now let us delve into these CFT aspects, and we'll start from what we have already studied. So we want to learn from and use Nielsen's techniques in case of conformal field theories. So we want to basically geometrize the problem of finding a unitary that takes us from a reference state to some target state. And as we had also seen, that we want to write a general unitary in this form, that is u tau would be written as path ordered exponential, where we would have this h gamma as our Hamiltonian, which we want to optimize in such a way on the group manifold of unitaries, so that we can get the minimal number of unitary gates that we would use to reach the target state. So as I have written here, the Hamiltonian H is we would look for the optimal choice by finding a minimal geodesic on the space of unitaries. And let me go on. So metric on the space of unitaries have different choices. For example, we could choose different cost functionals. For example, we did choose something different, which we called maybe F1, F2, and there were penalized version of these called FP and FQ. Typically, F1 is called a one norm metric, and F2 is called a two norm metric. F2 is more of closer towards a Riemannian geometry. It takes us closer to Riemannian geometry approach. And so in case of CFTs, what we would see that the universality of two-dimensional CFTs stem from their obviously the stress energy tensor generating the Virasoro algebra, but we know that there are two copies of Virasoro associated with a CFT, but we'll focus on, for example, a single set of Virasoro, actually a single copy of Virasoro, and we would focus mainly on the symmetry groups of the Virasoro, or symmetries of the Virasoro that are governed by, for example, the Virasoro group that are in 2D CFTs, and express complexity in terms of the CFT central charge. That would be our sort of a goal. So this techniques that I'm going to talk about are mostly based on a paper by Kaputa and Xavier Maran, and this came out in 1807. But more recently, actually, these things have been that was sort of a starting point, but I would say that it was still there were arbitrariness about how to approach, or how to approach to a some exact calculations or things. But very recently there appeared 2 or 3 papers which also dealt with, for example, instead of Virasoro, one of the papers dealt with Kachmudi algebra. Another paper dealt with the same approach that these people followed, but showed some examples where they could actually perturb the CFT reference state and found solutions of certain equations that we are going to meet at some point, come across at some point. So let me go on then. And so unitary circuits, as we said, that for two-dimensional CFTs, most of the symmetries can be realized, or the universality of the CFT stem from the stress energy tensor, which generates the Virasoro algebra. So we will basically construct unitary circuits by exponentiation of the stress energy tensor operator, and we will work with CFT 1+1 defined on a Lorentzian cylinder. So we will work with cylinder light cone coordinates tau and sigma, where the circle would have a unit radius parameterized by sigma. And as I mentioned already, that we will deal with one copy of Virasoro. And by complexities, what would we mean here are we would assign cost rather than complexities. We would assign cost to unitaries u tau on a representation of the group of diffeomorphisms on the circle that takes this sigma to some other function f sigma, or when we change the tau coordinate consistently. So let me be a bit more specific. I'll be a bit more specific as I go on. So this u tau corresponds to a group element f tau sigma that maps the circle to itself. So we will, as I mentioned, that I will start from a unit circle and we want to map it to itself by some function of group element of Virasoro, which basically represent the sequence of diffeomorphisms of sigma interpolating between, say, identity. Let us consider that the point that we start from our reference state, let us assume that f0 sigma is simply sigma, which is similar to saying that u at t is equal to 0 is identity. Whenever we have sigma, just sigma, we would call that area identity. And maybe at tau equals to 1, we assume that we reach our target state. For example, we would say our target state is psi tau equals to 1, psi 1, let's say. So in that case, if 1 sigma, we will denote it by f sigma, and it is similar to u t equals to 1 that we dealt with while considering this free field theories, equals to u target. So this we have previously seen these e to the power minus ih tau d tau things acting. So when it acts on a general element u tau, it actually takes it to some u tau plus d tau. And so here I would like to remind you that this h tau would be formed by the set of unitary gates or universal not set of gates, but generators of the gates and certain control functions gamma tau. And this sigma is different from the sigma that we talked about a little bit earlier. I have just noted this to make it clear that to our earlier notation, the sigma is in general different from the sigma of light cone coordinates, cylindrical light cone coordinates. And so since this u tau and e to the power minus ih tau, where there is not an integration yet, for a given tau, it takes it the u tau to u tau plus d tau. These are called instantaneous gates, this h taus. And Xavier Magan proposed that to study the submanifolds associated to symmetric groups. For example, here we would have a Virasoro symmetric group, and for any element belonging to the Virasoro group, we would denote the unitaries by actually the unitary representations of the group elements G. So UGs, whenever you have a element G, you would have a corresponding unitary representation of that element in the group itself, and that we will consider as being the unitaries. It will become clearer as we go on. So similar to this instantaneous gate action in case of a general Hamiltonian, the homologous group action would be sort of you take a element at a particular tau and you want to take get the element at tau plus d tau, then you do it by simply taking e to the power q tau d tau element group product, where the q tau is simply, I have just written this as this thing, minus ih tau is q tau, and this is a Lie algebra element in the appropriate unitary representation of this group element g tau. So we would deal with they work with basically reference states they take as energy eigenstates of a primary with chiral dimension h, and that the density corresponding density matrix would look like this simply. So this is a pure reference state that we start from, and ideally we should, although in this paper they considered say general density matrices, but ideally we should go to target states that are pure as well, since we also saw that the unitary gates that we typically used for representing a target state or reaching a target state that can only take you to a pure target state. So although they talked about in this paper about by dealing with density matrices, ideally I would think that for a mixed state you would need some more involved calculations, for which you need to also take into consideration the purification scenarios when you are at a mixed state, or when your target state is a mixed state. So let's say the target state, as we saw earlier also in the case of free field theories, that typically on the matrices that denote that mark the space of states, the unitaries act in this way on the matrix part. And so here in this paper, they particularly, as I already talked about, they wrote the relation in terms of density matrices, but one has to look whether for example, it might be that these tau matrices, that the target that marks the target state density matrix, it would also be a pure state density matrix, and there would be subtleties involved whenever you consider a mixed target state, which they haven't considered in their paper. So the cost functional choices, as I also mentioned in case of free field theories, there are two typical choices when you haven't yet introduced the penalty factors. One is called one norm and one norm metric, and other is called two norm metric. So for the one norm metric, you're given a density target state density matrix, and your q tau that I denoted earlier, that takes you to, for example, at tau plus d tau. You'd write this cost functional choice f1 tau as in this form, trace of rho tau q tau. This is very similar to, so for example, q tau is similar to minus I tau, which in our from a notation that we had long back, it would be something like gamma tau, that is control functions, and set of universal gates. Let me write it, gamma I tau and sigma I, where the sigma is our universal generators of the unitaries. And so these are independent of, I mean, these do not change with tau. And so all of these q taus are basically controlled by the change of control functions with respect to the tau coordinate. And you sort of take a, this rho, multiplying this rho tau is simply taking a product, or sort of taking a norm of this different gamma tau i's. You would take a norm of this, and so this can also be written in this form as well, where you simply, since this is a trace, you could always write the rho tau as u tau, rho 0, and u dagger tau, and you could take the u part in the right hand side, since this is a trace, and then you could write in terms of the reference in density matrix, and all your tau dependence would go into this q tilde tau, where the q tilde tau is simply u dagger tau, q tau, u tau. So similarly, one can denote the two norm metric in this form, and here also one can write it in terms of the reference density matrix and the q bar taus. Okay. So learning from this and following this, start from Virasoro group elements that and the group elements should follow certain properties that we, of course, expect them to follow, which are obviously the sigma coordinate is 2 pi periodic. For the maps also, it should follow the same thing, that if sigma are the map that takes from sigma to some target state, and this f sigma plus 2 pi should be so it should be 2 pi periodic, and it should also be invertible, which in other words means the derivative with respect to sigma should be greater than 0. And Okay, so let us consider that the group product given by the composition, group product is given by the composition in the Virasoro group elements, f dot g equals to f composition property into G. And the in 2D CFTs, of course, as I also mentioned probably earlier, that we have 2 copies of Virasoro, which appear as the transformations of the cylinder light cone coordinates sigma and tau. And in Hilbert space, these diffeomorphisms are represented by acting different unitaries or different unitaries UF, where you change basically this function f of sigma. If you change f of sigma, you would get different diffeomorphisms which take your initial state to different target states. And this UF, so obviously this these are basically equivalent to taking some conformal transformations, and this UF, in other words, gives you the well-known transformation of energy momentum tensor with Schwarzian derivative. So in general, if this function should be dependent both upon tau and sigma, and for each tau we have one diffeomorphism, or for each tau we have a different f sigma. For example, at tau equals to 0, we would have f0 sigma to be sigma, which let us call this f0 sigma, and let us call it tau equals to 1. We reach at our target state where the f at 1 comma sigma is, let us keep it arbitrary at this point, and it would be f1 sigma. So here the q tau primes in this unitary representations, the unitaries are represented in this way, and the q tau primes they belong to the Virasoro Lie algebra. So now let us try to write what we mean by this q tau prime, or since all the unitaries basically mean transformation of the energy momentum tensor with Schwarzian derivative, we would want to write it in terms of the energy momentum tensor itself, or it might be a good idea to sort of look at the energy momentum tensor as your what should I say, the unintegrated version of energy momentum tensor as your generators of the Virasoro group, or the group of unitaries. So the choice that they make is simply they take q tau to be this thing, d sigma over 2 pi, where sigma is integrated from 0 to 2 pi, and epsilon sigma tau sigma, and t sigma. So here, as I have written it here, this t sigma like universal, not the universal generators of the universal gates, and as you can see,
Aranya, your voice is breaking a bit.
That you okay? So
I think it's a bit better now. Can you just repeat for last 30 seconds?
Okay. So what I was saying is that the q tau is written in this form, where the t sigmas are considered to be similar to something of the generators of the universal gates, or the UF that we have here, which are the Lie algebra elements of the Virasoro group. And this part is sort of, in this part you see that the epsilons would have tau dependence after you do the sigma integral. So they are sort of representatives of the control functions that actually are, in case of computing the circuit complexity, we sort of saw that these control functions are sort of the sort of velocities on the space of unitaries. So you have on the manifold of unitaries, you would get these control functions to be storing the information about the velocities at or tangent vectors at different points of the manifold. And this in turn can be written in a discrete version in this way, where you Fourier transform both your t sigma and epsilon tau sigma in this way that I have written here, where the ln's form the usual centrally extended Virasoro algebra that I have mentioned here. But let me just, given the time, I will just talk about mostly the results, what they get from this ideas. And of course, so by using this inverse relations of ln and epsilon and with t sigma and epsilon tau sigma, you can get back the thing that we started with. But since we already saw that the way the unitaries act on the density matrices in this way can be reinterpreted by saying that these U's act on actually the Q taus, by which we got this Q tilde taus to be U dagger Q tau U. So if we input that in here in this representation, you would get that Q tau Q tilde tau. It comes like this, and it's simply like it is simply every unitary gives a conformal transformation to the energy momentum tensor. So one finds that one can write this transformation in a general form where of course there would be a Schwarzian derivative term and there would be this term where, and this whole thing will be multiplied by f, what should I say, f prime to the power -2, where f primes denote a partial derivative with respect to sigma coordinate, whereas whenever I write f dot, it would mean partial derivatives with respect to the tau coordinate. So for Virasoro symmetry gates, if we want to fix the dependence of epsilon, whatever we had as control functions in our Q tau representation, how do they really act on the f function? So the easier way to represent it is similar to what we saw, that the HT or the Hamiltonians were considered to be instantaneous gates that takes a unitary to some of time tau to some other unitary of time tau plus d tau. Here also this epsilon basically takes your f. This is again the group composition operator or group composition action. Here it takes your f tau sigma to some f tau plus d tau sigma, where as an infinitesimal version you could take it to be like this, and you could also write this thing as that I have written here, because we are just making a infinitesimal transformation of d tau. We could of course write it in this form: f tau sigma plus up to first order del tau f tau sigma. And by writing it in this way, you would realize that actually the del tau f tau sigma is realized by this epsilon tau sigma acting on this f tau sigma d tau. D tau comes in the right hand side already, because this is a general, this doesn't involve a group composition operator, but when this epsilon tau sigma acts on the f tau sigma, what it does is basically changes the sigma coordinate to some, instead of this sigma, it will basically become, you would replace it by f tau sigma in here. And so your general del tau f tau sigma would be written in this way: epsilon tau, but the second argument would be changed from sigma to f tau sigma and d tau. So similarly, yeah, so you can write it in this form as well, and where, for example, here we had in the left hand side we had sigma, but in the right hand side we had f tau sigma. So if we do inverse kind of thing, when we write sigma in the tau part, then we should in the same kind of relation, we should really write the del tau f second argument of the del tau f to be something else than sigma, or which should actually be the inverse of this thing. So when it was f sigma, it was sigma. Now when it is sigma, it would be something like inverse or F inverse tau sigma, and that is represented by this capital F tau sigma. Or you could also understand this by saying that this capital F takes your F tau sigma to sigma or inverse, and this thing can be written in this concrete form where there shouldn't be a del tau over del sigma, this F's. So and one can show that the symmetry circuit that they considered is quite general. If you just take, we represented this Q tau as some multiplication over epsilon and T integrated over d sigma, sigma coordinate. So if you take just the bar, so this is, I have written it here, it is different from the Q tilde. This is simply just taking the Q bar, and you could write it in this form, where your 2 pi h sigma, small h sigma, is just T plus its antichiral part, and also 2 pi p sigma is just the complex conjugate part when subtracted one. And in principle, for using these, you could write the CFP Hamiltonian and momentum in these forms, where your Hamiltonian would be simply L0 plus L0 bar minus C over 12, and your momentum would be L0 minus L0 bar. So if one does this and one takes again the reference state to be a pure eigenstate of CFT Hamiltonian created by a primary operator with chiral dimension H, and I should mention that it also seems like a natural choice, since the basis of CFT can be obtained by acting on this reference state with different strings of ln operators, or the generators of the elements of the Virasoro on this H. So the task that remains after this parts are simply to employ the Virasoro algebra and use the transformation properties of the energy momentum tensor. And if one uses that, the one norm metric comes out to be of this form: C over 24 d sigma f dot over f prime. Again, f dot here means derivative with respect to tau coordinate, and f prime means derivative with respect to sigma coordinate. And the part inside bracket is 2a square plus a Schwarzian derivative kind of thing, where the 2a square is simply this thing, and it is all can be derived from simply the things that I have mentioned in here. That is, you use the well-known transformation laws of the energy momentum tensor, and you employ Virasoro algebra with that. And what they were able to show is, when you take the two norm metric, it remains same up to leading order of central charge. That is, it remains f1 tau itself. So the change of different choices of cost functionals that sort of changed your main result in case of circuit complexity in free bosonic field theories. Here you see that at the large central charge limit, f2 and f1 gives you sort of same cost functionals, and they are equivalent. But it's not yet, I should mention that it's not yet the complexity that we want to calculate. This is just the metric that you want to look at. But to compute the complexity, you have to again take a d tau integral, and for all taus, you should minimize the whole cost functional thing. So that's how you represent it in here. You have to take a d tau prime integral again from 0 to tau, where, for example, if you are saying that we reach the target state at tau equals to 1, then you could take the upper limit to be 1. So, and it, as they have found in their paper, that there are simple and meaningful optimal protocols for finding a minima of this CF tau for SL2R with vanishing Schwarzian derivative. So it happens that the Schwarzian derivative part only contributes to a phase factor overall phase factor, a complex phase factor to be precise, and they call it, they at least argue that this is irrelevant for the complexity notion, because this phase factor simply is like doing an identity operation. But of course, there are also some other proposals where people say that, not really proposals, but questions where people question that whether this phase factor could be related to something like a geometric phase, or this should have some information or non-trivial information which we shouldn't just throw away. But in different cases, again, in the more recent study that I mentioned, which involved the central extension and also Kac-Moody algebra, there also they find the same thing, that the Schwarzian derivative sort of contributes only a phase factor, whether that is, and they were also unable to really extract some useful information out of that phase factor. So, and so this is a scenario which, if you don't consider this part, then it is not that hard to compute this thing. And again, the thing becomes even easier if you consider a diffeomorphism for which f dot over f prime is constant, just C1, then you would have to just optimize this 2s to these two integrals to be precise, and it simply becomes C1 EH tau, where the EH is mod of H minus C over 24, and which is expectation value of the energy momentum tensor, the EH is. And so in this simple study for the class of path where f dot over f prime is constant, one again finds that the complexity grows with time, because this is again becomes proportional to tau. Okay, so, and again, we built only a single copy of Virasoro. Instead, if we had dealt with 2 copies of Virasoro, then the actual complexity of the CFT should look like one be considered, and another copy which considers some, maybe in general can be some independent conformal, analogous but independent conformal path for the other Virasoro group. And yeah, so this is what I had in mind, but I can go on for a little bit unless you have some questions. That would be mostly okay. Let me make 1 or 2 more comments, which should just be that the one norm metric is they explain or interpret. There is an interpretation where the one norm metric is related to the Berry connection or Berry phase, Berry connection to be precise, and the 2 norm metric is related to 2-point connected correlators of energy momentum tensor in this picture, where what we really consider is conformal transformations of the energy momentum tensor. And the problem boils down to considering different conformal transformations, and how do different conformal transformations would give you different target states. And again, so these were this is the study that these people did around maybe 2 years ago, but the more concrete versions of these came more recently, in probably May, where Michal Hiller and Mario Flori, they considered the same problem, but they considered a Fubini-Studi metric, for which they compute as the 2 norm metric F2. In case of F2, they simply take a Fubini-Studi metric, GFS, let's call it GFS, and it is simply Fubini-Studi metric is related to measuring some overlap between a space of states, and it is also related somehow to fidelity susceptibility. So for this choice of metric, they have some results for a particular infinite or perturbative transformations of from the sigma coordinate to some sigma plus epsilon into sine m sigma, this kind of perturbative changes, and they have exact results for those things. So in that case, when you consider the Fubini metric, the problem really becomes ultimately the problem of finding geodesic, because the problem of solving a second order integral differential equations, and people have also commented about this being related to the Euler-Arnold methods and different for different choices of some variables in the integral differential equations. You could get KdV, CHS, and different kind of equations that you encounter in CFT literature. Yeah, so but this is a more recent paper, and here they have one example for which they have, using a Fubini metric, they have been able to get the complexity for a perturbative actual perturbative change to the sigma coordinate they have taken into consideration. Yeah, so that's all I had in mind about saying today.
Okay, so I think first we should unmute ourselves and thank Aranya for the entire lecture series.
Okay.
So we have
Yeah.
some time for questions. So please go ahead. Any questions, comments? Okay, maybe I can ask a tangential question.
Yes.
I don't know. So I think you also mentioned this, that this Fubini metric, I think, appears as some measure of entanglement also, right?
Yes, but I'm so basically what this means is you take the sort of overlap between, you can write this thing as 1 minus g tau tau d tau square plus d tau cube, and whatever you have, that is essentially your g tau tau thing. So there are some relations with this Fubini metric to Fisher information, where you have sort of the space of states that you are dealing with is trivial, or there are operators that commute to each other. You can relate this Fubini metric, or rather fidelity susceptibility, to the Fisher information metric. There are some holographic proposals as well as some notions in field theory where people have this intuition. But in general, I would say, it has some relations with it.
So my question was actually not that. I mean, my question was a bit sort of tangential. So the question is as follows. I mean, so the Fubini metric is a natural Kähler metric in the projective Hilbert space. So yeah. I mean, I just always had this question: does the Kähler structure play any role in this context, or is it that it just so happens that a Kähler metric is a natural thing to describe? I mean, because let me put it this way: that, for example, the other place where, for example, Kähler structures comes very naturally is when, for example, you study compactifications or certain moduli spaces of supersymmetric theory. So there, for example, the deformation of Kähler structure actually encodes some physical information. So the fact that this also turns out to be a Kähler metric, it probably is a very sort of tangential question. But has anyone sort of tried to play around by deforming the scalar structure, working with a different scalar metric and see what you get?
No, I think I personally, whatever literature I have gone through, the idea I got is they simply took this Fisher information metric as one choice, since you could also write this Fisher information metric actually in terms of the previous choices of F1 and F2 that we had. And this can also be written in this choice. And also another motivation is that this also is related to the general overlap of states where you perturb a state a little bit. So this is how the Fisher information metric really came into this picture. But I last time I actually heard some people where, for example, Kaushik Rai and his group, some people were, I think, looking at the complexity things from Kähler perspective or Kähler structures, but I don't yet know whether they have they haven't yet reported something. So people haven't really thought from this perspective complexity yet. Yeah.
Okay. Karan has his hand raised. Karan, go ahead.
Yeah, I mean, I might have missed this part, but can you just tell me, does the central charge have any role in your analysis in considering the CFT2 that you're considering?
The central charge through the, of course, the central extension and the.
No. Do you, what I mean by that is, do you take it to be small or large or anything like that, or it has no dependence?
Oh, no. In this calculation, it doesn't really play a role. But when you calculate the two-norm metric, you see that the calculations show that if you expand it in terms of the central charges, the two-norm metric can be written as the one-norm metric plus 1 over C correction. So if you go to the large central charge limit for the CFT calculations, the different norm metrics give you the same result, which sort of washes out the ambiguities that were present due to different choices of this matrix that we had in case of free field theories. In case of CFTs, if you consider large central charge limit, this ambiguity washes out, because you have, in terms of expansion over C,
what
you would have the two-norm metric.
Ambiguity are you referring to?
So if you, so if you had taken, in case of the free bosonic field theories that we considered, which we could take different choices of cost functionals or these F1, F2, and they would give us in general different results. For example, one you'd have to minimize something, and for another case you would have to minimize something, which in general the both minimization procedures, the result do not give you the same thing with the same basic set of gates, and the universal gates that you use are same. The everything else is same, just this functional changing gives you different results. But for conformal field theory, the structure is so that if you take the large central charge limit, they are the F1 and F2 give you the same result.
Okay, so how does this affect the final complexity answer? You're saying that you get the same complexity answer, but there is no ambiguity regarding the cost function. That's your statement?
Yes. So you could take different cost functions, and if you take the large C limit, then you would end up with same complexity.
Okay, so see, I find that a little
example, here
confusing.
What they say is,
but
had you,
I find that a little confusing, because I would have thought that complexity in some sense should capture should also be a reflection of the density of states in some sense, in the sense of I mean, if you're in small values of C's, you should have one notion of complexity, and if you go to larger values of C's, you should have another, because the density of states increases.
So in case of F1, really you do have only a single term. You cannot really expand it with
say that
in terms of C.
There should be different complexities depending upon, or I mean, the notion of complexity, how complex it is to go from one state to another should have some dependence on C. But you're saying that through this Nielsen approach, this is not true. It has
no. It has dependence upon C, but So the first term is sort of is proportional to C.
Yes.
It is also proportional to C, and F1 and F2 when they are equal, in both of them are proportional to C. But
by
had you
choice or by some what is the argument for this?
No, they just come in this picture by the when you use the conformal transformation equations or conformal transformation laws of the energy momentum tensor.
Okay, good. Yeah. And
yeah, so in case of F2, just it happens that you have a for example, with this F1C, you have something which is, let's say this is some F1 prime, which is actually is
I see.
one dependent.
I see. So your whole answers are set up in such a way that I think it is talking about large C in some sense. Like you've not made a real comment on small c, or small c has not been considered fully in this. Like you're suppressing.
Small c, for example, you could consider for any C, these things would be for small c anyway. This could be the then maybe the contributing part that really.
Okay.
Yeah.
I see. Yeah. Okay. Thanks.
Any other questions or comments?
Aranya,
yeah.
Probably you said I missed it or something. So when you're doing this CFT, and also what are the role of primaries and descendants? Have you discussed that? Or?
Yeah. So I haven't really mentioned that. So that is something. So the complexity calculations in CFTs are yet very in its early steps, and it's taking baby steps. So in the appendix, or rather the outlook part of the recent paper that came out in May by Mario Flori and Hildar, they mentioned that there are some calculations by some people where so basically their argument is that when you take into consideration the primaries, and also so I have mentioned here that the reference state is typically a energy eigenstate of a primary of conformal dimension H, chiral dimension H. So if you take descendants into consideration also in your picture, then it might be that to reach a state you could get some kind of shortcuts. They say shortcuts, and it is something related to a work done by Vijay Balasubramaniam and collaborators, in which they talk about chaotic Hamiltonians constructed out of the conformal primaries and descendants. So the comment that these Hiller and Flori make in their paper is that there might be a way to maybe if you include the descendants into the picture, that you could get to the complexity, or you could get to the target state with a lesser complexity, or that might be a shortcut in a way.
Right, because what I was thinking is, if you have this primary and descendants, so your target is actually from starting from given a state, you want to go to some target state, right? So what I was thinking, that if you have the primary and descendant, you can divide the whole setup, like the whole space, in terms of Virasoro modules, and then you can, if you know what particular descendant or something where you are, you can just even combinatorially, probably combinatorial description of complexity is also possible, because then it's just from a primary to a descendant, it's just some set of I mean just some LMLN operators, right?
Yes.
Okay, so that's and also one more probably again. So you are also using this. You are also having the bosons, right? Three bosons or something.
Here we just start from a state of energy eigenstate. Here we haven't really considered.
You are not okay. Because you also said something about the Kaczmarzyk thing, right? You said people are.
So the Kaczmarzyk thing was also done really, and probably during the lockdown the paper came out, probably in April or May, probably in April, and it was so it's really so so for example, they revisited the problem of really including the central extension of the Schwarzian derivative into consideration. They calculated the thing keeping the Schwarzian derivative terms, and so and they revisited the problem of the complex phase factor that appears. So they probably, the conclusion of them, as far as I remember, is that in case of Virasoro, these Schwarzian derivative terms do not play a, or do not give you any physical information to Frank. But in case of Kac-Moody algebra, you have to deal with the centrally extended thing and keep in consideration the keep in your calculation the Schwarzian derivatives as well, because there they give some physical information about the things happening in the space of unitaries.
I'm sorry, I didn't quite get that. You're saying why wouldn't the Schwarzian play a role in the generic case? Because your entire basis is that you're talking about the diffeomorphisms playing a role, right?
Yeah. But the Schwarzian derivatives
saying...
in here, the calculation at the end of the calculation of complexity always gives you a so phase factor only, a complex phase factor, which is which can be intuitively understood as it really doesn't change your state much. So
what do you mean by it doesn't change it much?
I mean, it sort of, it's if you consider a state and the same state multiplied with a complex phase factor, which is in the complexity picture, they consider it to be the same state, and you have to just operate with the identity operator. So
okay, I see. So you're saying this is by definition they say that they don't care about the phases. Is
yeah, the phase factors are So in the I will list down the papers that are regarding these things, which discusses these things. For example, there have been probably 3 or 4 papers only till now in the Slack, and you can look at them, and there are more details in there. For Kac-Moody, the Schwarzian derivative plays a role, and there it gives you some information arguably about the things.
Okay, that sounds fantastic. So I think we are already 10 minutes past 12:30. So let's thank not only Aranya, but Aranya, Urpita and Pratik, all lecturers for this complexity topic once again.
Yeah, thank you. And yeah.
So let's let me pause the recording. Okay, we'll come back to the post-lunch session. Adwait will continue telling us about info loss problem in ADS2. Over to you, Adwait.
Okay. So let me just quickly summarize what we did in our last lecture. I showed you a very quick derivation of Schwarzian. So we started from a JT gravity, and JT gravity was completely reduced to its boundary manifold. And the only physical degree of freedom was where you place the boundary manifold. And that degree of freedom is called Schwarzian mode. And the action for different configurations is given by Schwarzian derivative of that function. And that's the Schwarzian, that's the famous Schwarzian action that you get for JT gravity. One more thing I would like to say is it only comes in the UV of the theory. So if the boundary manifold is not very close to is not asymptotic, but if you just push it in, then the action is not Schwarzian, it changes. Second thing we discussed is once we find out what is the shape of the boundary, how do you detect presence of horizons? So basically, if the as I had shown here, if these curves end at some finite bulk times, from those finite bulk times you can just draw 45-degree lines and consider those lines as your horizons, because regions outside these 45-degree lines cannot communicate with your boundary of your space-time, and hence that defines a horizon. Third thing we saw is how to prepare thermophile double, or how to prepare equivalently. So thermophile double is something that you prepare in the field theory, and an analog in the holographic dual bulk, you prepare a Hartle-Hawking state. So we saw that how do we prepare these things using Euclidean path integral. So basically you take Euclidean path integrals on circle and you cut them across some line, and that prepares so if you cut a circle, it has 2 endpoints, and those 2 endpoints define a state in a double copy in in a Hilbert space which has two copies of an identical Hilbert space, and that state is considered to be thermophile double, and so which is just given here. And a similar ADS bulk of that prepares a Hartle-Hawking state where all along the bulk slices you do gravitational path integral and prepare a state here. After that, we saw that just an idea of how do we couple these this ADS black hole to a boundary, because ADS black hole on itself does not evaporate. So you want to couple it to some auxiliary system where the radiation can leak into, and such that there is a way you can see that radiation escapes the ADS part. And just conceptually, we thought of I told you that you could do it using just attaching a half flat space to either side, and there are 2 points of view to look at it. One is you either can think of it as a CFT, which is the lower diagram here, CFT1 coupled to a CFT2 on a half line, or you can just replace CFT1 two CFT1s by its corresponding holographic dual, which is the black hole. So the assumption is the two CFT1s are in thermophile double state, and that's why the bulk dual is a eternal black hole. So you can either look at it as CFT1 coupled to CFT2, or you can look at it as or you can look at it as a black hole coupled to these external flat space times. Okay, so as a so the lower diagram, if you don't put CFT2, that's fine. Then it's just a half line, and at let's say this direction is sigma. Then all you can say, and so here also the direction sigma goes in this direction. So I can call this line as sigma equals to 0. So it's just a manifold where the only degrees of freedom are at sigma equals to 0. So it's a manifold whose boundary has a CFT1, and I have not yet put CFT2 in here. Okay. And then above manifold, what all I have done is replace CFT1 by a corresponding manifold in the bulk, which is the eternal black hole, which is this ADS region here, and the outside bath region remains the same. And in today's lecture, I'm going to make this more and more precise. So last thing we saw is what are the coordinate patches for a Poincare-Reporoff plane and Rindler patch. So the complete brown patch here, the shaded brown patch here is a Poincare wedge, and is described by these coordinates which are given up here. And if you have and if you consider a Rindler solution, which is the black hole solution, so the exterior of a black hole, or the exterior of this horizon, is called the Rindler patch, and that Rindler patch you can go from that. So okay, so the Rindler patch will be described by y coordinates, and Poincare wedge all of Poincare wedge will be described by x coordinates. So the top equations here are describing all of the brown shaded region, and it's described by x plus x minus coordinates. And if you do these coordinate transformations, where x plus is tan hyperbolic of pi by beta y plus, and similarly for minus, that's whatever I've written is a right transformation, in the sense it's a right Rindler wedge. There's a similar left Rindler wedge which sits here, and I can write down a similar transformation for such a Hilbert space also, but then I have to transform it from the left Poincare wedge. And then the coordinates and the dilaton in the Rindler patch look as this expressions at the bottom. Okay, they're in y plus y minus coordinates, and y plus and y minus goes to infinity and minus infinity on these horizons. Okay, these are like tortoise kind of coordinates that we describe in Schwarzschild black hole. So now what I wanted to tell you today is that if you want to construct a space-time a manifold like this, it is completely how you can construct it really. So how we can embed. So I would like to embed all of this into a flat manifold, and the point to take away is that the manifold that I have constructed here, that I took an ADS2, and then I took an ADS2 black hole, and just attached two half flat patches to both sides. all of this manifold is conformally flat. So that what does it mean? It's just I can start from a flat manifold that is just Minkowski manifold, flat space, and I can do a while transformation and conformal transformation to get to this patch. Okay, and I'm going to start describing that now.
Sorry, there's a question from Subbu.
Yes.
Yeah, Adwait, so you did two things over this ADS2 black hole. So one is like introduce this bath, which was fine because you wanted things to leak out. And the second thing is you said you'll put CFT2 on the whole system. So why was that done?
So
physically?
Maybe I should have been more clear. So one thing, I did two things. One thing is I attached a manifold. I just attached a flat space time. Okay.
Right.
And then I'm saying that now I'm going to put a CFT2 on this. Okay.
What does that mean?
So
I have CFT2 on it?
I have given you a manifold and you just have to now describe a CFT2 on this manifold. So you can describe CFT. Yeah.
I could do that. But what does that mean for the ADS2 that we originally had?
Yeah. So see, if you don't have any field on a manifold, there is no Hawking radiation. Okay. You at least have to have minimum, you have to have graviton peaks. So that at least gravitons radiate. But now gravitons are harder to handle. So I'm putting some, I want to put some other field which will do the job of radiation, which will do this pair creation. And that field for me is going to be this CFT.
I see. Your Hawking derivation is in that CFT now.
Oh, yes. Yeah. So
I see.
Hawking radiation is this CFT2.
I see. Okay. Yeah. Thanks. Yeah.
Okay. So let's start by so let me start by describing how do you start from this manifold.
Just a clarification.
Yes.
So the CFT2 is on this entire big diamond.
CFT2 is on the entire big diamond. Yes.
I see. Okay.
All right. So the this big diamond is just a flat diamond. So it's just described by the usual flat metric. Okay. So now what you can do is you can do these transformations. So let me write down these transformations here as W plus minus is equal to
Adwait, sorry. This might be a bit naive, but like if we have like, so when we are doing the Hawking derivation, right? So we are doing it in this flat 2D spacetime or in the ADS spacetime?
Well, they are related by while transformation and conformal transformation. So I can derive it in flat space and then just transform it to see how it looks in the.
I see, but okay, but maybe I missed it. But is that in the whole spacetime? Like, is this only a patch of like Minkowski, this ADS2?
Yeah. So the manifold which is here is only a patch of complete Minkowski diamond.
Yeah,
right?
okay.
It's only that part. So the red parts are not there.
Right. So no, I'm just confused because this seems like the Hawking radiation is coming out of like horizon in a Minkowski spacetime. As in like in Minkowski spacetime, I mean there is of course you can do the Unruh effect, right?
Yeah.
But but when you have black holes, the Hawking derivation is usually because of like black hole horizon, right? But here it seems like it's coming from the Rindler horizon. Is that correct, or am I missing something?
That's kind of correct what you're saying, that it will come from the Rindler horizon. But so all I'm saying is that we want to construct a manifold which looks like a black hole connected to a flat space. Okay. And now I'm saying that this manifold can be embedded into a flat space.
Yeah, that is fine.
Right. Okay. So ideally, I'm supposed to do calculations in the manifold I constructed. Right. But just because calculations are easier to do in flat space, I'll do the calculations there and then just do the coordinate transformations to come here. See, doing conformal transformations and while transformations do significantly change the stress tensor in some sense. So it's doing something non-trivial, even though in 2D it's quite trivial.
I think I have a related question, I think.
Yes.
So in ADS2, you had these boundary slices, right?
Arindam, sorry, Karan had raised his hand before you.
Oh, okay.
You mind? Yeah.
Yeah, just a quick question. This Y is describing the gray area, is it?
Y, so the, yeah, so the coordinate transformation I have written down right now. Y will actually describe both gray and blue area.
Okay.
Right. So in earlier patches, when I was drawing here, Y was just describing the yellow region, but I can extend the Y outside also to the, when I connect the flat space out here, I can extend the Y coordinates to them also. And that is just very nicely done here, because it's basically just a Rindler patch in a flat space.
Okay, yeah, thank you.
Yeah.
Yeah, Arindam, go ahead.
Yeah, sorry. So in ADS, you had these boundary slices, right? Which basically gave rise to these horizons depending on their shape.
Yeah.
So what is the interpretation of those slices in this big flat
So
space?
the thing is, there is, this boundary manifold is still here. So maybe I should, yeah. So the boundary manifold is still here, right? It's the tan hyperbolic solution.
Yeah,
it's still here. So let me, yeah. So the thing is, okay, in this manifold, this line which I've drawn here is really a fake, in the sense there is no singularity there. You can in principle extend the manifold just beyond like this. So okay, the real manifold should look completely like this, you see. So, or this is too complicated, but let me try to explain what is happening here. So the original manifold that we imagined is, so let me outline it by reds now, or let me draw a wiggly line. Okay, so this is the manifold that we imagined earlier. Okay, but the point is that these lines here are not there, in the sense manifold doesn't really end there. So you can extend the manifold along these lines. The ADS black hole manifold, okay, the ADS black hole manifold can be extended just as a vertical strip, and then you are just attaching these two wings to two sides. Okay, now all that I'm saying is that I know a bigger manifold, which is this diamond, which goes like this. Okay, which can describe the exterior of a black hole and the external wings. Okay, and this brown thing that I've drawn is really a Poincare wedge. So okay, let me get to this point maybe slowly in order to understand. But did I answer your question? Maybe I'm not sure.
I mean, yes, I understand that in ADS2, in order to derive this, for instance, these equations for the boundary, right? It was important that they are really very close to the boundary of ADS.
Yes.
Right? Because you omitted all the higher order terms and so on and so forth.
Yes.
But the flat space structure of the boundary is very different. So, I mean, I don't understand in which sense these are still like boundary slices.
No, so you can see, the thing is, you can assume, okay, so let me draw a diagram here, so if this is your eternal black hole in ADS, okay, and what this really means is there is really a boundary curve here. Okay, so the actual space-time was quite big. It extended all the way up and down, but what happened is your boundary curve ended somewhere. And because your boundary curve ended somewhere, you have these horizons. Okay,
right.
That's the description I told you. Now, in principle, what you're really supposed to do is not, so your manifold is supposed to end at this point only. So whatever I'm shading should not be even considered in your manifold. This is not a part of your manifold. The blue line is your boundary of the manifold. Okay. Now what I'm really doing is that if I take a flat space, which is like a Minkowski diamond, right? And Minkowski diamond, I cut the Minkowski diamond slightly inside here. Okay. And then this is the shaded region, and just pick this part up. So now delete this from the flat space, pick this thing up. Okay. And just plug it in here. Do you see what I'm doing?
Yeah.
So I'm just attaching, I'm cutting the flat space so that it gets attached there automatically. That's what I'm doing.
Right.
So and in principle there are quantum fluctuations in these boundaries. So the boundary of ADS has quantum fluctuations, but those exact fluctuations are what are called graviton fluctuations, boundary graviton fluctuations in 2D. And there was an elaborate argument, not elaborate, very small argument I tried to give in order to convince you that those fluctuations could be ignored. So if I can ignore those fluctuations, then this boundary is a stable classical object. And now I can just attach a flat space to both sides. Okay. But just for drawing, now once I know that this construction is done, I can just forget about whether there is a line here or not. Okay, it's not very important where the cutout is, but it's quite close to the boundary. So there is really some sort of epsilon limiting thing here, but it's not really important. And I'll maybe show how, when you connect the metric, where you have to connect the, you have to show that the metric coming from ADS side smoothly connects to the metric to the flat side, right? Otherwise, manifold will have some singularity setting somewhere. So if you do that, you'll see that it's not connected exactly at this vertical black line, but it's connected slightly inside. So let me just start describing the coordinate patches, and maybe it will be more clear. Okay. So if you do,
may I ask a question? Sorry.
Yeah, sure.
Go ahead.
Sure.
Yeah. So the question is, you said that you're putting a CFT2 on this bigger Minkowski diamond.
Mm-hmm.
So this is a naive question. So, but the system that is inside has a scale, right? I mean, it has this RADS.
Yeah.
Isn't that inconsistent with the CFT or CFT2? I mean.
System that is inside has a scale. You're saying manifold has a scale and it's inconsistent to put CFT2 on the manifold? Is that the thing? I mean,
yeah, I'm not so familiar with CFTs, but my naive understanding.
I'm saying you could do something like this also, right? So you can put a CFT on a cylinder, and that also has a scale, like radius of the cylinder. But probably that just turns out to be the temperature. So it's some sort of, yeah. So it's, if a CFT has a scale, that's okay. Yeah, if manifold has a scale, that basically turns out into the. It's basically saying I've put a CFT, but I'm working with an excited state, and that excited state has some local energy density in it, and that is that scale.
I see. Okay.
Right. So okay. So the coordinate transformation from W to Y I have written here. Go from W coordinates to Y coordinates, and Y coordinates describe the blue region plus gray region. Okay. And let me write down. So I'll only try to write down the right diamond, right blue plus gray diamond, and this is how I'll write. So let's see. Yeah. So first of all, the coordinate system. If I say R means the whole diamond on the right hand side. Okay. This R. Okay. R is the right hand side. Blue plus gray patch. And that patch, if you do this coordinate transformation from W, you will end up here. You'll get this 4 pi by beta squared e to the power 2 pi by beta I think y plus r, y minus r, dy plus r, dy minus r. Okay. So this is the coordinate system that describes the right hand side gray plus blue patch, and we have already seen that on these slices where so on the horizons and on the asymptotic boundaries, y's go to infinities and minus infinity. Okay, so y plus probably increases this direction and y minus increases this direction. Is that what happened last time? Yeah, good. So this is what it does. But we know what the metric of the Riddler patch is, and this was given here. So this metric here is what describes the Riddler patch. Okay. So if you look at it, it is also conformally flat in the sense it has dy plus dy minus, but it has a wild factor attached to it. Okay. So what I have done now is I've shown you that I can get to from W plus W minus, I can describe the blue and gray region by this coordinate system, but this is not the coordinate system that I want. Okay. So after this, I do a while transformation. So let's do so first of all, these transformations I have written down are conformal, right? Just by the fact that W plus is a function of Y plus and W minus is a function of Y minus. These are, I mean, if I complexify it, these are purely analytic and anti-analytic functions. So these are conformal transformations. So what I did was from get to W to Y, I did a conformal transformation. Now I'm doing a while transformation. Okay. And that while transformation just does this. So what does it do? The while transformation's job is to remove this conformal factor. Yeah. So the while transformation's job is to remove this conformal factor from this and replace it with the correct conformal factor, which is this, which is 1 upon sine hyperbolic square. Okay. So let me write down an equation. The equation basically is this. So now what I'm doing is I'm writing down a metric for only ADS region. In the sense, this metric is only valid for the right gray region. Okay. And for that, I basically have to do this. So I have to, okay, so let me probably try to call this as some omega 1. Okay. So first of all, I have to get rid of this factor. So I have to get rid of this. Okay. So, and then I have to plug in the correct factor. The correct factor is minus 4 pi squared, beta squared, sinh minus to the power minus 2, pi by beta, y minus r, y plus r. Okay. And multiply this whole thing. So this is, and multiply this whole thing to the ds square r. Okay. So you see what I have done? I started from W, then I went to a coordinate system, dsr square, which is describing gray plus blue. But now I'm doing a while transformation. So what I have really have to do is that I have to do a different while transformations for the blue region and for the gray region. Okay. So if I do so the transformation I am describing right now is only for the gray region, and that exactly gives me the coordinate chart I want. It exactly reproduces this coordinate chart which I described to you before. Okay. So this is, so the point, you can work it out. So maybe it might be hard to follow equations, but the only point I'm trying to make is that you can start from W coordinates, do conformal transformation to describe all of blue plus gray, and then you have to do different while transformation for blue and a different while transformation for gray in order to exactly get the metrics that you want. Okay.
Adwait?
Yes.
I think Shubham raised his hand. He has a question. Shubham, go ahead.
Why are you saying that different parts of R should need different while transformations? Because this ds square R is for the entire R region, right? R ADS plus R bar.
Yes, yes, that's true.
But
the
yeah.
manifold I constructed before here, right? Here the gray part is ADS. So the metric there should look like an ADS black hole metric. And the blue part is flat. So let me explicitly write down what metrics I expect to be there. Okay. So maybe that's what I should have done before.
Oh, I see. You want to while transform into a metric which looks like ADS.
Exactly.
I see. Oh, okay. So, you don't just want to get rid of the sine hyperbolic factor.
No.
Yeah,
so this is what I want to do. The gray part here should be, okay, so let me write down exact metrics and that might be easier. Okay. So the metric of the blue part should look like this. ds square is equal to minus 1 upon epsilon square. So maybe delta square, dy plus dy minus. Okay, this is what I want the flat patch to look like. So I'm keeping this small conformal factor here for the flat patch. And this part I want to look like this. I want it to look like 2 pi beta square dy plus dy minus divided by sine hyperbolic square pi by beta y minus y plus. This is what I want to do. This is the manifold I desire. Okay, but the thing is, what I'm trying to do in this slide here is I'm trying to start from a big Minkowski diamond, and I'm showing that I can go to that manifold, but just by doing conformal plus Weil transformations.
And like, is this thing well? I always thought, like, I mean, Weil transformation of a metric should be like, it can't be done patch by patch. Maybe that's wrong, huh? Like, I mean,
well, the Weil transformation itself should be continuous across the
right. Okay.
So the Weil factor itself. So if I'm writing
I see.
writing my whole metric of R as some omega to the power minus 2 dy plus dy minus, then this Weil factor itself should be continuous across that point.
I see. So you will find a way to stitch it up.
Yeah. So I'll just describe it here itself. So this is what I want. If this is what I want, then basically when y minus plus y plus, sorry, not plus, minus. Am I writing it correct? Yes. And I'm dropping the subscript R. Okay, but just we are describing the right patches. Let's take this thing to delta. Okay. What is this? So y minus, this is basically the y1 coordinate. Okay, y1 coordinate in the sense, so this vertical line here is y1 equals to 0. Okay, and y1 is negative, so y1 is negative in this direction, and y1 is positive in this direction. Okay, so there is a minus sign difference here, which we can, so it's probably minus sign here. But okay, anyway, so just take this limit. What you will see is sine square in that limit. Just so the whole thing should just become yeah, it should just become pi by beta delta whole square, right? The denominator factor here,
yeah,
in this limit should become this. So it will cancel the factor of pi by beta square, right? So maybe there is a factor of 4 needed here because it's a plus minus coordinate, and plus minus probably are defined with y0 plus y1 by 2 or something like that. Okay, just some factor problem. But then what this does is when I do this cancels this whole factor, and then this metric approximately just becomes dy plus dy minus by delta square, which is exactly equal to this metric.
Right.
And then I match it at that point. Okay. All right. So there are metrics defined differently. So the ADS metric can be smoothly connected to a flat metric, provided you put this conformal factor in the flat metric itself.
And one more thing, like maybe this is a bit vague, but like, I mean, it's like you want ADS metric by Weil transformation, right? I mean, you could, for example, somebody else could do get some other metric also, but the analysis possibly won't change, or will it?
So okay, the thing is, if you when you're going to put CFT2 on it, okay, and then all the vacuum formulas for CFT2 in a flat space are very well known. So the log of length formula of entanglement entropy, which I had described earlier, is the vacuum state CFT2 formula.
No, I'm saying for RADS.
But what I'm saying is these conformal transformation plus Weil transformation have definite meanings. So conformal transformations is just if you do a conformal transformation on a state, it just keeps you in the same module, same module of the vacuum. But if you do a Weil transformation, it can change the modules. So it genuinely, so you have to basically see. I mean, I'm saying what you're saying is correct. Yes, someone else can do different things, but the more important thing is how it's going to affect your CFT.
Yeah, so that's what I'm asking. Like, it will definitely affect your CFT and therefore the analysis.
That is right? That is very important, and we will come to that. So, okay.
Adwait?
Yes.
So there's a couple more questions. First, Rohan, and then after that, Subbu. Rohan, go ahead.
Yeah. So this stitching that you do is basically, so your full manifold isn't Minkowski in the gray plus blue patch, but you want, like, as you approach the gray region, it should be ADS, and as you approach the blue region, you need it to be flat.
Yeah.
So this artifact, so this particular stitching you have to do because you're, had you, for example, come from a higher dimensional black hole, it would have been apparent. Like this particular while factor would basically be like the dilaton.
It will automatically be smooth over a long time.
Yeah, and this transition would basically mean that in fact this while factor is actually the dilaton's behavior in the full thing. For example, if you take 4D extremal black hole and figure out what the dilaton behavior is at extremality throughout the black hole, not just in the throat region, it will have this kind of a behavior where it smoothly goes into the gray region and the blue region. So now that you're not coming from top down, you have to like artificially do this. So that is the thing, right?
Okay. You have to connect it like that. So okay, so I hope I'm going to give
Subbu is 1 second. Subbu's next.
Please, go ahead.
Yeah. So okay. So this analysis. So let me confirm if I got it right. So every 2D metric is locally conformally flat, but the subtlety here is probably that across the boundary you want the conformal factor to match. Is that correct?
Yes, that's correct.
So I'm also wondering, I mean, this might be related to all the things I don't know that Rohan just said very quickly. So like, how would it work in like higher dimensions? Because like, I mean, here I know that given any metric, I can do a conformal, I mean, Weyl transformation and get to that because every 2D metric is conformally flat. But does this process generalize to higher dimensions?
Can I just quickly answer that?
Sure.
So you can take any extremal solution in like 3, 4, 5 dimensions.
Yeah.
Dimensionally reduce so that only R and T remain.
Yeah, sure.
And read off the value of the dilaton.
Yeah, sure.
So basically, the dilaton would be sitting in like in JT kind of this thing. The dilaton is basically sitting in front of the metric.
Yeah, that I understand. Yeah.
So that is basically the while factor. And
but what I don't understand is like if I start with, let's say, some ADS3 black hole.
Yeah.
Then I get an ADS2, right? Like when I dimension.
Yeah. So when
how do you get the blue region?
So the blue region, so you get an ADS2 or you get a 2D manifold. Okay. Now, if you the analysis is that you are when you're doing the Kaluza-Klein reduction, you can choose what the 2D metric, how the 2D metric multiplies the dilaton. So it is not just the restriction of the 3D to 2D. You can also choose the conformal factor, and that conformal factor. So when you're doing the usual Kaluza-Klein dimensional reduction, you have an option of what the 2D metric should be, and you can multiply it with an arbitrary value of the dilaton. Okay, and you set it appropriately. Here the setting is as if it comes out right when you're doing the near horizon JT physics. And now your 2D metric will basically look like it will not look ADS2 throughout. But in the near horizon region, it will look like ADS2 multiplied by this while factor, which remains constant in the throat region. And it blows up outside the throat region. So when you go close to the horizon, it looks like it is just ADS2 multiplying some dilaton, which is constant. But if you analyze this value of this dilaton field in the full black hole, it will look like it is some constant in the throat region, but slowly starts varying and becomes such that it becomes flat in the such that the effective 2D metric becomes flat.
I see. Maybe on Slack you can put a reference on this.
Okay. Yeah. So so what I showed is that if I want to get to R ADS metric, I have to start from W coordinates, do a conformal transformation, and which describes all of gray plus blue region, and then do a separate while transformation for the gray region and do a separate while transformation for the bath region. So basically the bath region while transformation is quite simple. All you have to do is to construct the bath, all you have to do is first of all remove the original while factor, which is bracketed here in red, and that I have removed, and then just put 1 over delta square, because the bath metric is just simple this metric dy plus and dy minus. Okay, so now what I have showed you is that the manifold that we wanted, that a flat patch attached to a asymptotically ADS or eternal ADS black hole can be exactly constructed starting from a flat space, or it's equivalent, it's conformally flat, it's equivalent to a flat face up to a conformless Weil transformations. Okay, so good. So now what we want to do is let's put CFT2 on this, all of this manifold. Okay, if you want to put CFT2 in all of this manifold, so okay, manifold is well defined, so we can put a CFT2 on this. And now let's look at how do you look at preparation of states in this manifold. Okay, so if you remember before, what I had said is that thermal field theories are circles, and if you cut states along a diagonal, you prepare, on the field theory you prepare a thermophile double, and on the bulk you prepare Hartle-Hawking states. So let's see what happens, what is a similar construction for the model that we have constructed. So what we have now is we don't have just a circle, because we have a CFT1 coupled to a CFT2. Okay, so there's a CFT1 on a line, which is the blue, okay, which is the line here. Okay, and the blue region is the CFT2 on half line. So basically the model is this, that there is a dot, and then there is a line, and there is a half line, and on the dot you have a CFT1, and on the line you have a CFT2, but it's on a half line. And if I want to put this model on a circle, it basically looks like this analyst thing, where it's a half line, but I have conformally compactified it, some tan transformation. So the width is pi by 2. So this is how it looks. Okay, and now the only thing that is holographic is CFT1. So the dual to that looks like a this right hand side manifold, where all I have done is replaced CFT2 by its dual, which is the Euclidean black hole. Okay, so a thermal CFT1 dual to that is a Euclidean black hole, and I have filled up the space in the middle. And now this is the complete Euclidean manifold, which is dual. So the manifold that I've drawn here is a Lorentzian manifold. Okay, but what I've drawn here is a complete Euclidean manifold of a thermal theory, which I want to construct. Okay, now I do the same thing which I did earlier. I just cut it across a diagonal. So on the CFT side, so when I say CFT side, it's only CFT side of CFT1. Okay, because CFT1 is the only thing that has holographic duality here. So you, on the CFT side, it creates a TFD. Okay, it creates a thermophile double of CFT1 coupled to CFT2. It's a thermophile double of CFT1 coupled to CFT2, and corresponding bulk dual is a complete Hartle-Hawking state of the complete theory. Okay, this is the construction. Now you can take these states and then you can analytically continue in Lorentzian time, and this is what happens. So if you analytically continue the CFT, it just gives these things, and then again I have conformally compactified the flat spaces. So flat spaces don't do anything because they don't have holography, so it just goes up as it is. On the right hand side, if you see, I have replaced the CFTs by its corresponding Lorentzian and Euclidean bulks, and you can see that it creates a black hole. Okay, which generally happens. So I mean, so the brown picture, brown patch in the right hand side model is known to us. This is how generally an eternal black hole is described. But this all I have done is just attached a blue patch, or external bath, and the part below this green line is a Euclidean manifold, and part above here is a Lorentzian manifold. So it just and then all you have to ensure is that on those green lines, you can glue the metrics, because you can show that the Israel junction conditions are followed, and you can glue the metrics across that line. Okay, so this is the
question. Sorry, there's a question from Subbu.
Yes.
Yeah. So Adwait, how do you write this thermophile double state in CFT1? I mean, of CFT1 in CFT2. Like in CFT1, I know how to write thermophile double, but
I mean, I don't know how to explicitly write it, but it's just a construction where you say that if I have a CFT1 coupled to CFT2, and if it's on a circle, if I cut it across some point, it's going to give me a thermophile. See, what is a thermophile double? Thermophile double just says that if I have a theory and it has an energy spectrum, then I just create a copy of it, which let me call E tilde, and just do this object, right? Beta by
yeah.
Right. So this E now is a combined energy eigenstate of your CFT1 plus your CFT2 plus some coupling.
I see. Okay.
So
Yeah,
this
that
E is a combined CFT1 plus CFT2 energy eigenstate, and now you're constructing a combined thermophile.
I see. Okay. Thanks. Yeah.
Okay. So now something very nice happens, and that nice thing is that, so let's look at this diagram here. Okay. So what I have said here is that the state on this line, which is at t equals to 0. I'm just darkening it by red. The state on this line is whatever is dual to a TFD. Okay. So on the field theory of CFT1 coupled to CFT2, we created a TFD. Now whatever is in here is basically some Hartle-Hawking state, which is dual to the TFD that we had constructed in the field theory. Okay. It just happens, and I'll tell you why this happens, but it just happens that this TFD is also the ground state, is also a vacuum of the flat space. Okay, so if I put so let me again say what I'm saying. If you prepare your imaginary manifold here, which we had constructed, the top diagram, okay, and at t equals to 0, you have prepared you have put a CFT2 first of all, and then you have also put that CFT2 in a Hartle-Hawking state, which is dual to the TFD, which is dual to the thermophile double. Okay, so you have prepared a CFT2 in a Hartle-Hawking state. So it's a state where right and left modes are completely coupled. This state this state is exactly equal to the vacuum of the CFT that will be described in all of this diamond. Okay, why does it happen? So let's first look at what we are looking at. So first of all, I did not probably emphasize this a lot, but the black hole solution is really, so okay, roughly how did the equation of motion look like? So the equation of motion for the dilaton looked something like this. Okay, which is approximately some G Newton. Yes.
Surbi has a question. Surbi, go ahead.
Yes, please.
Yeah, Adwait, in the previous slide, like the point that you mentioned that this thermophile double state is dual to the Hartle-Hawking state on a certain line.
Yeah.
I mean, I don't understand this. The thermophile double also has the CFT2 states.
Yes.
So how can a 2D ADS be dual to the CFT2 part of the thermophile double?
Sorry. Yeah, I understand what you're saying. It's I see what you're saying. You're saying that the state in the bath region is just the same state, right? Okay, so let me say this again. So let's look at the 2 points of view. 2 points of view are first is that there is a state on this manifold. Okay, and so this is what I call a 1D point of view, and then there is a point of view where it looks like this, where these dots would have been at these points. Okay, but I've replaced the dots by the manifold in the interior, and this is the 2D point of view. Okay, and this is a particular spatial slice that I'm looking at. Now, here in this, what is happening? There is a CFT1 here. Okay, and then there is a CFT2 here, and the CFT2s here are on just half lines. In this manifold, what is happening is there is a CFT2 all across. Okay, so the thing is, the state that these CFT2s are living in is a different state than this CFT2 is in. Okay, so the what happens when you go to the dual picture is that there is a necessary interaction between CFT1 and CFT2 here. Okay, at these dots. So dot and the line edge of the line are really interacting with each other. Okay, but in this picture here, in the 2D point of view, such interaction does not exist. The CFT2 is just freely allowed to move along the manifold. All that happens is minimally coupled to the gravity. In the sense, it's coupled to the metric. That's it. So if you just look at it, the Hilbert, the state here, the TFT, is in the Hilbert space of CFT1 times Hilbert space of CFT Hilbert space of CFT2 on a half line. Okay, but this here is a state on a state of just a Hilbert space of CFT2, but on this hybrid manifold. Okay. So the point is, the Hilbert spaces are quite different. The Hilbert space here is this Hilbert space, and that to CFT is on a half line, and the Hilbert spaces here is just CFT on this weird manifold. And in that sense, they are dual to each other. Okay. Did I answer your question somehow?
Okay, so it's not a holographic duality.
No, it's not. It's yeah, it's not a holographic duality. It's some sort of hybrid holographic duality.
Okay, thanks. Yeah, that was my confusion.
Okay, so
there's a question from Rohan also. Rohan.
Yeah.
Can you go back to that last thing? Yeah. So here on the right hand side, it should be the CFT2 plus the gravitons, right? The Hartle-Hawking would have all those light gravitons.
Yeah, plus gravitons, exactly. Yeah, CFT2 plus gravitons. So I don't know, plus gravity. Okay. So okay, now this is what I want to do. This is the equation of motion, and then the solution, black hole solution, which we were looking at, is really a solution of T mu nu equals to 0. It's a vacuum solution. Okay. So if it's a vacuum solution, what does that mean? That means that, so first of all, which part we solved it? We solved the equation in a Poincare patch. Okay, so we had a Poincare patch, which basically looks like this. This is a Poincare patch, and that Poincare patch is described by this wedge here. This is the right Poincare wedge. Okay. Which maybe if I want to highlight it, it is this region. Okay, I hope it's clear. This region is where the Poincare patch is, and if I solve for stress tensor equals to 0, that means whatever matter I put, if the matter is in matter stress tensor is 0, then the solution is black hole. Okay. So what I have to ensure, whatever happens when I put CFT2, my black hole solution should not get destroyed. Black hole should remain black hole, right? So if I want to say that the black hole solution always should say black hole, that means all along this slice, okay, yahan pe, in this region, which is the ADS region, I'm supposed to maintain that the stress tensor. So as I said before, this region is what is just being described by x coordinates. So x0 is T Poincare, okay, and x1 is z. So x coordinates. So the stress tensor in x coordinates of the CFT2 should be 0. This is the condition, right? Because I don't, even if the black hole was a vacuum solution, and when I put CFT2, I didn't want to destroy the black hole. I want to keep black hole as black hole. Hence, the stress tensor generated by CFT2 should be 0 in the ADS region, in the X region. Okay. Now, but what you can do is, if you just do a coordinate change, which I had said before, to go to Y coordinates. So let's go from X to Y coordinates. Okay. And if you go to X to Y coordinates, obviously, so the X to Y coordinate change was this. It was X plus minus equals to tan hyperbolic of pi by beta, Y plus minus. Okay, this is a conformal transformation, and we exactly know how stress tensors change under conformal transformation. Okay, so what really happens is Ty plus plus minus minus is equal to Tx plus plus minus minus, which is really 0. So this part is really 0, but I'm just writing for completeness, you basically have to write it as this. So let me not write plus minus because you understand what it is. Schwarzian of x as a function of y. Okay, so that means that if all along the brown region the stress tensor is 0 in x coordinate, then if you do this coordinate transformation, you'll see that there is some stress tensor which is only inside the green region. Okay, and that the value of that stress tensor is just given by this equation here. So what I want to do is I want to put this as 0. So the stress tensor in the x coordinate is 0 because I want to maintain it as a black hole solution. So wherever black hole exists, the stress tensor should be 0 all along that patch. But the conformal coordinate transformation will show that there is some sort of, because exterior of the black hole in the coordinates which describe exterior of a black hole should have some thermal factors into it, right? Hence, if you only focus on the y coordinates, which is the green region here, you'll see that there is some stress tensor. And that's just a consequence of conformal transformation, this Schwarzian kind of transformation that stress tensor has. Okay. Now, we also want to construct a model where black hole does not evaporate away. Black hole stays as it is, right? So if black hole stays as it is, it should not exchange energy with the bath, or it should not, the radiation should not really leak out. And so the scenario I want is radiation should leak out and exactly same amount of radiation should also come in. Okay, maybe not the right color. So what I want is if the radiation goes out, exactly same flux of radiation comes in. And what that tells me is that so maybe I should put an index here. So this is Ty of ADS. Okay, so Ty in the ADS region, in the sense the green region. Okay, and I'm saying that I don't want black hole to change its size, so there should be no net energy flux across the boundary of ADS. Hence, I'll keep Ty plus plus of the bath, meaning the red region here, is equal to Ty plus plus of the ADS. Okay, which is the formula basically here. Okay, so now I have exactly given you I have told you what the state is. I've told you what the stress tensors are in different regions, and now I've and basically you would say that, well, how can you make this, right? Because there's already a while plus coordinate transformation defined. So how can you get rid of this? So the
Can I
point
ask you a
is,
question?
yes, please.
So didn't we want the energy to leak out of the ADS into the bath?
I don't want a net flux to go out.
So what does that mean? I thought the energy should go into the bath and you were observing some.
Yeah, but I want same amount of energy to come back. I want to describe an eternal black hole where the pair production keeps on happening.
Okay, thanks.
I don't want to describe an evaporating black hole. It's not of interest to me. So that's the point. So you see, you can always ask then what is the difference, right? Before, what was happening was radiation was going to the infinity and then it was bouncing back. Now what is happening is radiation is going out, but same amount of radiation is coming in. So first boundary condition is a reflecting boundary condition at the boundary, and the second boundary condition is transparent boundary condition. But if the flux is same, what is the difference? So the point is, these kind of things do cause a difference while computing very fine-grained things like entanglement entropy. Okay, so it does matter. So the scenario before, the equilibrium before was achieved because the boundary of ADS is repulsive. Whatever radiation was going to the boundary, exactly same amount of radiation was falling back in. But now what is happening is the radiation is really escaping the boundary, and then same amount of radiation is also falling in. Okay.
Rohan had a question.
Yes.
Rohan.
Sorry, pass. I pass.
Okay, Karan has a question. Karan, go ahead.
Yeah, I'm very sorry. I actually got a call and I think I missed this part. Maybe you mentioned it, but how are you imposing the last box which you wrote? I mean, I got your point till this Ty plus plus ADS. And now I'm presuming you're going to do the coordinate transformation you mentioned earlier, that given my metric in that green and red triangle, I can choose either the green one or the red one by some appropriate scaling.
Yeah.
So when I do this scaling, how do I recover that last condition that you wrote about, that
So
TADs?
let
How is
me
it a
start.
derived thing, or I mean?
So you have a W coordinate, and you can, from W coordinates, you can do a lot of things. First of all, you can go to the X coordinate. Okay, X coordinate is the so W coordinate is it is a complete diamond. Okay, so let me just put these. Maybe I should just add a diagram here. Not the correct diagram. Okay, so let's start here. So I have a W coordinate which describes the complete diamond. Okay, then I can go to go to X coordinates, which are the which is the brown region. Okay, then there's two other things I can do. So there's a transformation from X to Y, okay, Y ADS, and there's transformation from W to Y, but so Y to R ADS. Okay, so there is a transformation from W to Y, which is R, WYR. In the sense, this transformation describes. So in this diagram, it describes green plus red region. Okay, and this transformation just describes green region. Okay, now I can start from YR and I can do two things. I can start from here, and I can so let me also write what transformations these are. Okay, so coming from, okay, so let me just not talk about these transformations, but you can do them. So you have this. The first transformation from W to Y is a conformal transformation. Okay, now from YR to you go to YR ADS, which is just the green region, and then you go to YR path, which is just the red region here. Okay, this transformation is while. Both of these transformations are while. Okay, now the point is we have to know how the stress tensor really behaves under while transformations. So under while transformation, it does something like this. Sigma. Okay, let me not write it down. If someone really needs an explicit expression, I'll provide it later. What I want to say is, generally what happens is, if I do a conformal transformation, stress tensor always picks up this Schwarzian pieces. Okay, so stress tensor transforms a Schwarzian, and maybe I wrote something wrong in the last. Yeah, this whole thing also is multiplied by this conformal factor, which is dx by dy to the power -2. Okay, this is important. So what happens is, we know how stress tensor transform under conformal transformations. So first of all, let me tell you that when I said that in X coordinates I needed my stress tensor to have a 0 expectation value, so that this transformation which I had written here, if you do this transformation in reverse, you will see that if Tx is equal to 0, Tw is also equals to 0. Okay, so you should also have at t equals to 0, in all along this red line, the stress tensor is 0, and that's what I meant by it's a vacuum of the W coordinates. So it's a vacuum of the W coordinates, and that also transforms to the vacuum of the X coordinates, and hence in X coordinates you have the black hole solution, which is a vacuum solution. But now from W coordinates you do a conformal transformation, and that changes your stress tensor, and the conformal transformation just takes you to either green region or red region. Okay, after that you have to do while transformations. The point is while transformations are so trivial that they don't pick up any while anomaly. Okay, so the only thing you have to care about is conformal transformation. So the conformal transformations give you some non-zero ty in the ADS region, and it has to be exactly same ty in the bath region, and that's the whole construction. So now, yeah, maybe let me wait for another minute to if you have more questions, please let me.
Rohan has a question.
Yes.
Just to be sure, if I have global ADS
transformation which is taking you either to green or red, But my question is, how are you? Oh, I
No,
see.
hold
So
on. What's going
it's
on?
green or red. I see.
Sorry.
Okay. Thanks. Yeah.
Rohan, please go ahead.
Yeah. So if you have global ADS2 and if you had matter fields in it, under what conditions would the stress tensor be of the matter field be zero, like minimal scalar? Just global ADS2 or like Poincare ADS2?
I mean, under what condition you just whatever state you're choosing. So if you're choosing a state to be vacuum state, then it will be zero.
It will be zero, you're saying.
Yeah.
And
Or
I
if
just
you're
take
doing
like
some wild
Poincare.
transformation from that vacuum state, and if the wild transformation itself is trivial, so that it doesn't pick up any wild anomaly, then also it will be zero.
Yeah. So I mean, I'm just saying if it's just plain Poincare ADS2 and I put a solve for minimally coupled scalar on Poincare ADS2, and
Yes.
let's say I put some Dirichlet boundary condition for this thing,
Mhm.
then the stress tensor expectation value for the or the stress tensor for the matter field should be zero. You're saying?
Yeah, it should be zero. Yes.
It should be zero, right? Okay.
I mean,
Thanks.
if you put stress tensor, then there might be some dynamical thing that those things will start happening. Right?
Just at the probe level, I'm asking. Like,
yeah.
It would be zero, right? Because there will be you cannot support if you're imposing like Dirichlet boundary conditions, and you're assuming that the matter field dies down at the boundary of Poincare, then there is no way you can do that in ADS2. There is some such thing, right?
I think so. I have, yeah. Maybe I'm not understanding the question, but let's postpone.
Okay, I'll
this.
postpone it.
Yeah. We can come back to it. Okay. So now we have constructed the model and yes.
A question by Karan.
Yes.
Yeah, I just wanted to ask if there's any slice on that entire diamond, the large diamond, where your T is zero in its entirety.
Just red slice which I have drawn is where the stress tensor is zero.
Okay, so then the follow-up is you're saying then these temperatures on each side are like Unruh temperatures in some sense?
Temperatures on.
Or is it not to be thought of? Kind of?
I mean, they're Unruh from the perspective of looking at it from the flat space, but I'm not really interested in flat space. What I'm interested in is the manifold that I constructed, where there is ADS and then there is asymptotic.
I got that. I'm just having some confusion seeing how that temperature is realized on the red side. I mean, everything else is fine, but
temperature is realized on the red side is, well, it's not temperature, right? In the sense, it's some excited state that I'm using. So my state of the bath is really this belongs to this thermophile double kind of thing, which I had constructed by doing Euclidean path integral. So it's some excited state, and excited states have some average energy densities, which can be interpreted as its temperature, maybe.
Sure. And so, I mean, that's the part which I'm guessing it's okay. I'm sure that it's consistent and all. I'm just having just having curiosities on whether it matches with the Rindler construction exactly. Perhaps not.
Yeah, it does. The the W to Y coordinate transformations which I've given you are exactly flat space Rindler transformations. Left and right transformations. It's the extra while part which is curious, but again turns out to be non-trivial because it turns out to be trivial because it just doesn't generate any while anomaly. Okay, so we have this. Okay, so now from now on, I think I've told you how things are there, and I'll just be referring to this diagram. Okay, this diagram is the simplest diagram, where this is our manifold, and we are working with this manifold, and this manifold can be embedded in flat space. Okay, so every computation. Okay, what is the strategy? All the computations that I want to do in my manifold, not my manifold, the manifold that we constructed, I will first do them in flat space. Because in flat space, I've told you that the stress tensor in the W coordinate of the CFT is zero. That means CFT is in a ground state. So CFT is in ground state, and entanglement and computations and all the other computations are easier to do in those in a flat space. And then I know how, and also entanglement computations are just 2-point functions of twist operators. So if these are just 2-point functions, I know how 2-point functions transform under while transformations and conformal transformations. So the strategy will always be to compute a particular entanglement entropy of some region, do the computation in the W coordinates because it's easier, and then transform it back to the Y coordinates or whatever regions that you want to, and see what the answer is. Okay, so let's begin. Let's do the first computation that we really wanted to do, that Hawking did, which is what we started. So let's take, so first of all, the constant, okay, so the region, the coordinates here are, the space-like coordinate here is some y1r, and the and the space-like coordinate here is something like y1l. Okay, this vertical line is y1r equals to 0. This vertical line is y1l equals to 0. Okay, now and all of these coordinates increase towards right hand side. So y1r increases towards this side, y1l also increases towards this side, and they decrease towards the left side. Okay, and the constant y slices, constant y1 slices are given by these hyperbolates. Okay, and this is the infinity slice, and similarly that happens here. Okay, so y1l goes from minus infinity which is here, to plus infinity which is here, and then y1r goes from minus infinity which is here to plus infinity which is here. Okay, and that's how these two diamonds are being covered by y coordinates, by left and right separately. So let's begin. What do I want to do? So let's say I'm sitting in the exterior of the black hole, and I want to compute entanglement entropy of the radiation. Okay, how do I do that? The way I choose to do it is that I fix some y1l equals to constant surface. So let's call this surface as something like y1l equals to minus b. Okay, some minus b coordinate. And then let's also draw a surface which is y1r equals to b. Okay, so I've chosen two slices, I mean, I'm basically being at a fixed radial distance away from the black hole. And also keep in mind that I'm drawing these slices in the bath region. Okay, I'm not in the ADS region. Now, what you can do is you can just draw a nice slice, and I can just draw a nice slice which looks something like this. So it starts from here, it ends up here, and then again it starts from here, ends up here. And I'm just choosing it to be symmetric on both sides. Okay, now because black hole is radiating on both sides, I have to compute entanglement entropy of both sides, and then just take any slice that you want in the middle. Okay, I think one more small thing I have not really told you, emphasized on, is this, that if let's say this is a slice and you are trying to compute entanglement entropy of this region. Okay, but you could have also considered a different slice which exactly passes through the same points. Okay, and which exactly passes through the same points, and then you could also compute entanglement entropy along this that slice. Okay, then what is the difference? So the point to note is that the entanglement entropy doesn't really belong to an interval. The entanglement entropy really belongs to the causal diamond. Okay, so you can draw any other slices, all other space-like slices which go through the same endpoints, as long as the causal diamond of that slice is the same. The entanglement entropy will always remain the same. Okay, hence in our construction it doesn't really matter what nice slice I took. All that matters is where it ends. So these endpoints are more important than what particular slice I'm choosing to do the computation. Okay, so sorry. Okay, so that's why it doesn't really matter what slice I choose. Okay, so let's take this particular slice, and okay, and now let me introduce notations. So I'm going to call this region as BR. Okay, the right side bath region. Let me call this region as BL, and let me call the middle region as LR. Okay, I'm just saying it's a left and right system, and then left bath and right bath. So I'm calling LR in the middle because it's from the left SYK plus right SYK. Okay, so now what do I want to do? I want to compute this quantity. Okay, so let's be clear, and now I want to start color coding things, because yeah, it is okay. So whenever I am writing now, this model is also equivalent to doing this. Okay, so that the dual which I kept on, this is the 2D point of view. The equivalent 1D point of view is this, that I'm taking such a system and I'm evolving it in time, and I'm checking what is happening. So now look at how the interval is being constructed. Okay, the way interval is being constructed is that, so here also there are y coordinates. So there is a yl coordinates and yr coordinates, but they just end at y equals to 0. Okay, this dot is at yl equals to 0 and yr equals to 0. So YL, YL is negative in this direction and YR is positive in this direction. Okay. So the interval I'm choosing that I want to compute entanglement entropy of is the BL and BR. Okay. So what is BL and BR look like in this? So BL looks like this. So there is some YL equals to B region. And then I'm just taking minus infinity to this. And then I'm also picking, okay, not B, minus B, sorry. And then I'm also taking YR equals to B, and I'm taking that to infinity. So these are the two regions, right, which are bracketed by this yellowish color, are the regions of which I want to compute entanglement entropy of in the 1D point of view, okay, in the 1D point of view. But now in the dual picture, what I have done is I have replaced the dots by its corresponding dual, and that looks like this. Okay. So let's in the dual picture here, in the 2D point of view, let's try to compute entanglement entropy. So let me okay. So fine grained entropy, and whenever I'm drawing, whenever I'm writing objects with this color, these are always in 1D. See, I'm saying holography and all could always be shaky, but what is completely true is 1D point of view, because in 1D point of view, you have good old quantum mechanical systems interacting with each other, and quantum mechanics is good. So we don't have any problem in 1D point of view. So 1D point of view quantities are very solid. If you could do computations in 1D point of view, that means you have done the correct computation. Now we're trying to do computations in 2D point of view, but they have interpretations in 1D point of view because they're just holographic dual to each other. Okay, so a fine grained entropy of how do I put it? Okay, so fine grained entropy of minus infinity comma minus B union B comma infinity. This is what I want to do. Okay, this in the bulk. So the bulk quantities will always be white. Okay, this in the bulk is exactly equal to yeah. So as long as I'm in the bath region where there's no gravity, it's basically just simple computation of fine grained von Neumann entropy of the region BL union BR. Okay. Now you would say, what is the difference between these two? Because the intervals seem to be the same. The difference is it's a different state and it's a different Hilbert space completely, right? A 1D point of view has a thermophile double state. The 2D point of view has a completely different space and lives in different Hilbert space. But let's try to do this computation. Okay. Now let's also assume, which we want to assume always, is that unitarity holds in the 2D point of view. Okay. If unitarity holds, then the slice I have drawn all across, so the complete slice is BL, LR, and BR. The point is, all across this, the state is pure. It's a pure state. Hence, entanglement entropy, fine grained entanglement entropy of BL union BR has to be equal to fine grained entanglement entropy of LR. Okay. Is this clear? I'll probably wait for a minute for questions. But this I want to make. This is the logic that goes through. Okay. To just and yeah. Let me just stop. And if there are questions, please ask. Okay, no questions. Good. So we have a fine-grained entropy. So now instead of so this is basically like saying, so this statement right here, I don't know, yeah, this statement right here really is saying that the entanglement entropy, fine-grained entanglement entropy of the black hole has to be equal to the fine-grained entanglement entropy of the bath. This expression here is fine-grained entanglement entropy of the bath, and this expression here is fine-grained entanglement entropy of the black hole. Okay, so but it's the point is computing entanglement entropy of two intervals, union of two intervals, is slightly harder than computing entanglement entropy of a single interval. So instead of computing entanglement entropy of BL union BR, we'll compute entanglement entropy of LR. And I've already told you how you compute it. What you do is you do the computation in W coordinates. You do the computation in W coordinates, and then by using the coordinate transformation, you transform that answer to the Y coordinate. So let me write down a rough what really happens. So first of all, you do the computation in W coordinates, and then you do conformal plus while to come to Y coordinates. Okay, and that okay, I've given this coordinate transformations, so it looks like this. So S fine-grained entropy, and it's wide because I'm computing in the bulk of LR, which is also equal to S fine-grained entropy of BL union BR, is equal to this. So this formula was already known, C by 3 log of L by epsilon, where so now here is where epsilons enter, because there are conformal factors sitting in front of your metric, and your metric is not exactly flat. That conformal factor will be just interpreted as a cutoff, and that enters here, and the way it enters is this. So let me write down the formula. So W plus 1, 2, and I should have been more clear. Points here should be called, so this is like point 1, and this point is 2. And all that it cares about is where these points are located. So it's W plus 1, 2, and del Y plus W1 plus, del Y minus W1 minus. So there was a factor of there's a factor of epsilon of x, epsilon 1 of x, and epsilon 2 of x to the power half in the formula that I had given before. That factor is basically becoming these derivatives of w with respect to y, and we also know w plus minus as functions of y plus minus. Okay, this is known, I've given you before. So you do this computation, and if you do this computation, this is what you get. The fine-grained entropy of L union BR is C by 3 log of pi by beta cos 2 pi by t by beta. Okay, and then I expand this formula for t much greater than beta, and what I get is that this becomes 2 pi c by 3 beta into t plus some constants. Okay, and now here, this result here is what I had always been talking about. This result here is a linear growth of entanglement entropy. Okay, this is the exact same result that we had derived before, which I kept on talking about as n log 2. Okay, the pair production keeps on happening, and the entanglement entropy keeps on increasing forever. Okay, so this is we have done an honest to goodness calculation. We really did an entanglement entropy calculation in the bulk, and the answer we have got is where the entanglement entropy is just ever increasing. It just keeps on increasing forever. Okay, and this is Hawking's wrong result. This is what is called as Hawking's wrong result. So okay, any questions at this point? Let me wait for some.
Rohan has a question.
Yes. So this first you computed this thing in the entanglement entropy of LR in W coordinates, where in W coordinates it's flat, right?
Yeah, it's flat. So the
So
formula is
that
just C by 3 log of L by epsilon.
So So this is just so this is known. I mean,
This is known.
this is just the flat line
Exactly.
computation.
Zero temperature 2D CFT computation in flat space.
Okay, but this part also captures, but the LR region is mostly in the LR region is not mostly, it's entirely in this what's it the ADS2 part, right? The gray region.
Yeah, except this small piece which just sticks out.
Yeah, but it's mostly in that region. So
yeah,
so if I think of the W coordinate computation in that region, then it is also computing the entanglement entropy of gravitons in flat space in W.
No, now I'm only using the formula for 2D CFT, right? It's only the CFT 2D CFT formula. So I'm imagining that there are no gravitons. I'm imagining there are no gravitons here. I have a fixed background on which I have a CFT2, and I'm doing computations of those CFT2. So I know how to do computations of CFT2 in flat space.
Oh, so this is just the CFT2 contribution of the entanglement.
So CFT2 is what I want to interpret as radiation. So there could be graviton radiation, but this is a large CCFT. So contribution is enhanced by C, and the graviton contribution is at order 1. So it's suppressed over this. So I don't have to take graviton contributions.
But there is also this traditional computation of taking this thermophile double and stretching this entanglement entropy or this Ryu-Takanagi surface from one CFT to other. That you're not computing right now, because that is usually done in the ADS.
So
that's usually done in ADS.
We are still getting wrong results because we have still not used quantum RT prescriptions.
You're not. So you're still doing a proper this thing. So this is not to be confused with the Ryu-Takanagi.
Not yet.
Thing.
Not yet.
Okay, thank you. Thanks a lot.
So so we've got the wrong Hawking's wrong result, which I've been. I think I should go beyond now.
Adwait, Tushar has a question.
Yes, please.
He has written, I did not understand the complicated expression for the cutoff. How did you get that?
Oh, so
in the entanglement entropy for CFT2.
Yeah. So where do I do it? So basically, when the bath region was written as this, so R bath is 1 over delta square dy plus dy minus. This factor here is a conformal factor, and that factor is inverse of your cutoff. Hence, what I'm saying is the bath really has a cutoff, and that cutoff is delta. Okay. Now, if you write down a similar expression for the bulk, you have to interpret that while factor as a cutoff. Okay. So the thing is, there is no cutoff in the flat space, the W coordinate, but the cutoff, because W in the W coordinates, in the W coordinates, the metric is just dW plus dW minus. Okay. The while factors such as this appear in your metric when you do these conformal transformations to while transformations. Hence, the cutoffs are related to the while and conformal transformations, and that's how they basically enter as derivatives of those transformations, where W is a function of Y, and these derivatives exactly give you the conformal factors that stick front of the metric, and that's why it comes there. Okay. Yeah, maybe I'll try to write up some small this computation exactly and maybe put it on Slack. Okay, how much time do I have? Okay, so I don't have enough time to start something new, but let me tell you what is going to happen in the next lecture, and hopefully I finish it in the next lecture. Okay, so this is our space-time. Okay, and then what we did was we did a computation of entanglement entropy. But now let's look at it from the 1D point of view. Okay, 1D point of view is where there is a CFT living here. Okay, and for now, imagine that how do I do this? Okay, so maybe let me draw a separate diagram. So the 1D point of view is where you have a line and you have a dot, and where you have a dot on this side and a line. Okay. And the computation that we wanted to do, we did was this. Okay. What we did was a fine grain. So this is minus b, and there is some b here, and there is infinity here. So the computation that we did was,
Hi, can I ask a quick question?
just a minute, let me complete
Yes.
this, and after
Yeah,
that
yeah.
we can ask. So the computation that we did was the fine grain entropy in the field theory of minus infinity union minus sorry minus infinity to b union b to infinity, and this is what we computed holographically. Well, not really holographically, we just computed directly. Now that also implies in the 1D point of view as being equal to entanglement, because even in 1D point of view there is a pure state across these two systems, right? Hence this is also equal to the entanglement entropy of minus b comma 0 union 0 comma b. So maybe let me put subscript. This is from the left system, this is from the right system, this is from the left system, this is from the right system. Okay. Now if I want to compute this quantity, which is minus b comma 0, I really have to take this interval, right? I really have to take this interval here, these two intervals. Okay. And if I want to, so let me just rub it out, rub the initial intervals out. That means I want to do this. Okay, b comma 0 and 0 comma b, right? Now, while computing this, it includes the CFT1, which is a holographic system. Okay. So now, as I said before, so let me go to the prescription which I had introduced long time before, which is this, that if you have a CFT, and if you have a region of CFT, you construct Ruthaganagi, quantum Ruthaganagi surfaces belonging to those regions. Okay. Now, here I'm looking at a higher dimensional CFT, but if you look at our examples, which we are looking at right now, it's a 0-dimensional CFT. It's a 0 plus 1 dimensional CFT. So a space-like slice is just a dot. It's just a point. There is nothing else. There's no sub-region of the dot, right? It's already a 0-dimensional system. Hence, there is no other way. So the only sub-region you can consider is all of the system. All of your system is the sub-region, okay? A particular spatial slice, you just have to consider all of the system. So that means you're computing entanglement entropy of all of the system with something else. You're not computing entanglement entropy of the subregions, okay? That's one point. The point number one is that you're computing entanglement entropy of the all of the region, all of your CFT at a particular spatial slice. Hence, you can construct Ruthaganic surfaces corresponding to that, okay? So let's take the example that we were looking at, where there was a point here. I was considering some cutoffs here and then constructing, but the point is the dual, it might happen that if I start, let's say let's consider this, so I'm drawing a kind of hybrid diagram where the bulk also exists and the boundary theory also exists. The boundary theory is somewhere here, okay? And what it says is that if I want to compute the entanglement entropy of this dot, I have to compute area of the quantum extremal surface plus the bulk von Neumann entropy, which is encaptured in its entanglement wedge. It might happen that that entanglement wedge will just stop somewhere here, okay? So, okay, one more thing maybe I should say is that chi, which is extremal surface, is codimension to the bulk, okay? Our bulk is 2-dimensional, hence chi is 0-dimensional, okay? So chi, that means chi, the extremal surface is just a point, and sigma chi is 1-dimensional, okay? What does that mean? That the extremal surface is going to be some point in the bulk, okay? So let's say extremal surface is this. So this dot here is chi, and this line from the boundary to that dot is sigma chi. It's 1-dimensional entanglement entropy, 1-dimensional entanglement wedge, okay? And the boundary region B, which I had said B is all of your system. An entanglement wedge is captured between the boundary system and your chi. So 2 points enclose a line, and that's how it works, okay? So even the formula I had written is that the boundary of the entanglement wedge should be your boundary region union union the extremal surface, which is true here, right? The boundary of the line I have drawn is B, which is this system. The B is now all of the subregion, and chi is this the dot in the bulk. Okay, so once such things are happening, what it tells you that the dual to the boundary is not all of the bulk. The dual to the boundary is only its entanglement wedge. Hence, so I can draw a similar diagram from the other side, where the entanglement quantum extremal surface is here. Okay, what does that tell you? It tells you the dual to dot is only encaptured in these lines. Then what is really encaptured in this region in between? Okay, what I mean, okay, what is the boundary region from which you can reconstruct the region in between here? Because what entanglement reconstruction says that you can only reconstruct stuff that lies in your entanglement wedge. But now we are considering all of the boundary theory, and it seems that all of the boundary theory only covers part of the bulk. It only reconstructs parts of the bulk. Okay, then the parts which are not reconstructed by the one-dimensional CFT, who are they constructed by? Okay, and the answer to that is they are constructed by the radiation. They are constructed by the Hawking radiation. So the way once Hawking radiation is escaping, what happens is information of the interior. So and these regions which do not lie in the entanglement wedge of the boundary are called islands. Okay, so these regions are called islands. What it says is that once you start, let's say you start there's a black hole and then the evaporation starts. So initially, two field theories reconstruct all of the operators in the bulk. Okay, but as evaporation starts, what happens is some of the interior starts getting encoded in the radiation. So some part of the interior, which are called these islands, are not at all encoded in the boundary theory. In the sense, if I want to construct an operator sitting in this middle region, let's say here, I cannot reconstruct it from the CFT 1 degrees of freedom. The only way I can reconstruct them is from the CFT 2 degrees of freedom, which is my radiation. Okay, and this is the main concept. Okay, the concept is that when I said the wrong computation here is that this equation which I wrote here, that the S fine of BL union BR is equal to S fine of L equal to R, is a wrong equation. Why? Because the entanglement wedge of the dot here is only up till some point here. Okay, and the region in between is not reconstructed from the boundary theory. So the region in between is really encoded again in the radiation. I'll come back to it how it happens, but the thing is, this equation here is not exactly right. Okay, and to make it right, you can do something, but I'll come to that in the next lecture. Okay, now I'll take questions.
Subbu, go ahead.
So Adwait, so this is just about this large C thing. So in the bulk, because when you take large C, you can ignore the back reaction. So that is what enables you to do this double holography, is it? Because if it's a large CCFT, then
yes. So now I see. I mean, maybe I'll just say something here. So what is there is that you have a system where some part of the system is ADS and some part of the system is flat. Okay, but it's not really flat because this is really 1 by d delta square dy plus dy minus, right? And this has some very weird wild factor in the middle, but it is also conformally flat in the sense it's dy plus dy minus, but there is some conformal factor. Okay. And then the CFT2 which you have put on this manifold, if that CFT2 is also holographic, then it generates a third holographic direction. Okay,
I see.
And the way you embed, so basically when I said so this is what I was always saying, that there is a 1D point of view. The 1D point of view looks like this. There are two dots, and there is a CFT2 here, and there is a holographic CFT1 here. Okay, and similarly a CFT2 here. And because the dots are holographic CFTs, they can construct it. So this is 1D point of view. Okay, and this is 2D pointer. So because that dots are holographic, they can construct a manifold for you, and then you have a complete CFT2 here, CFT2 on this manifold. But now take this CFT2 also to be holographic. If this CFT2 is holographic, then it will generate a third direction, which we'll call, so which is generally represented like this. Okay, where there is a direction Z. Yeah, there is a third direction here, Z, and the actual boundary of the manifold is somewhere here, and this distance is delta. Hence, the metric here is 1 over delta square dy plus dy minus. And here, because you have a very weird wild factor, it cannot be at the same distance from the boundary, so it's at some complicated. It's basically at some embedded in your 3D ADS3. And this is the double holography, which is the 3D point of view.
Just a follow-up question. So this is specific to like 2D, is it? Like when you are in 2D, like you can go from 1D to 2D to 3D. When you are in higher dimensions, like this.
No, this can be done in higher dimensions also.
Oh, really? Okay.
Yeah, I think these constructions are called Randall-Sundaram constructions.
Okay. Thanks.
Surabhi, go ahead.
Yeah, my question was partly answered in response to Subbu's question, but I still want to ask, like in this slide that you had previously.
This one?
Yeah. So, are you going to use this 3D
no,
point of view to do the calculation?
No, it's not required.
Okay.
It's just that the island prescription, which I'll introduce in next lecture, is very obvious from the ADS3. It looks kind of ad hoc from the 2D point of view, but it's just completely obvious from the 3D point of view.
Okay.
I think that's why they first went to. So this is also a fun thing. Let me just tell you is that here to compute entanglement entropies, we had to use the quantum Ruth-Akeyanagi formula, right? But in the 3D, you don't have to use quantum Ruth-Akeyanagi formula. You can just use the classical version of Ruth-Akeyanagi, and it will still give you the right answers. That's what happens. So it's easier to do in higher dimensions than doing it in lower dimensions.
Okay, thanks.
Akhil, go ahead.
Hi. So at some point, didn't we say there's no energy leaking out of the ADS to the CFT?
No net energy.
But then when we did the calculation, what you called as the Hawking level calculation, we still got a rising entanglement entropy, right?
Yeah. So energy exchange can, so there is no net flux, but still entanglement entropies can increase. Oh yeah, I understand what you're saying. Let me make it clear. Yeah. So yeah. So what are we doing? Let's just try to reconfirm our initial picture. Oh yeah. Sorry. Okay. So the picture was that there are Hawking modes. There are Hawking modes going out, right? And the corresponding dual Hawking modes are somewhere in here, in the sense the things that they are entangled with. Okay. So first, let me draw the two slices. What we are doing is I'm trying to compute entanglement entropy of this subregion union this subregion. Okay. So first of all, let's look at t equals to 0 slice. Okay. So because it's a hyperboloid, t equals to 0 lies a bit behind. The point y1 equals to b at t equals to 0 is a bit behind. Okay. Now imagine a Hawking mode which lies. So there are Hawking modes which are here, and dual to that would be somewhere here. Not dual, sorry. And the mode which is entangled with that will be somewhere there. And there is a mode which is here, which is entangled here. Okay. So you see that this entangled pair is not captured by this surface. Okay. The only entanglement pair that's captured is this and this. Hence the contribution to n log 2. So maybe some color coding, right? So yeah, I think work. So the contribution to the n log 2 is only coming from the green pair and not the yellow pair. Okay. But now let's just go ahead in time. What happens is the green pair is still captured, but now the yellow pair will so green pair is still there. It's still captured by the entanglement entropy, and now the yellow pair will also get captured, right? So as the slice move ahead, it starts capturing more and more entangled pairs. And the same thing happens on this side also. There is a pair here which is not captured by the slice, but the same mode goes ahead and gets captured, and the entangled pairs to that are inside. Okay, so it's basically this is what is happening as the slice moves ahead in time. It starts capturing more and more modes, and their entangled partners are in the interior, and hence the entropy just keeps on increasing. And the resolution which I told you is that what you have to do is after some point you have to start including something called an island, which lies somewhere here, right? There's a region here which does not
I'm
belong to the
slightly confused. So
okay.
the entanglement is the entanglement is rising because your slice is changing. I'm sorry, I didn't get what you said.
Yeah, the slice is moving ahead up as time goes up, right?
I thought we were calculating the. Oh, okay.
It's a time-dependent entanglement entropy. So you calculate it at one slice, and then, I mean, you calculate it at all times, and you see how it behaves with times. So I'm just saying that as time moves ahead, there is so this is a constant B surface. Okay, as time moves ahead, the slice starts moving more and more towards y equals to 0. In the sense, it just looks like that in Penrose's diagram. It's not actually going there, but it just starts capturing more and more Hawking pairs. Okay, so first, when it did not capture these two Hawking pairs, there is no contribution from this pair. But as you move ahead in time, it captures one of the partner, and that's why it breaks the entanglement between these two pairs, this pair, and it counts. Yeah.
So any outgoing mode, I should think of it as being radiated by the black hole.
Yeah.
I thought, okay, they need not be like really close to the horizon or something. That's not.
Well,
at least inside the ADS part of it. Inside the ADS part of it, this seems to be like.
I think you have to do that. Yeah. Maybe this is a cartoon, not very accurate, because this mode switch I'm drawing could be just coming from the white hole. So yeah, something very close to the.
Okay, I think we have already 15 minutes past 4, and this is probably a good time to let us unmute ourselves and thank Adwait for his lecture. So let us stop the recording. Okay, welcome back. The last lecturer of today is Parthiv. He's going to tell us about S-matrix Bootstrap. Over to you, Parthiv.
Okay. So yesterday, I kind of concluded the analytic part of the Bootstrap. So in these two last lectures, I will try to catch up on this numerical work, because it is the numerical explorations that has happened in this I mean, in the modern setup, it is the numerical explorations that have been done quite well than the analytic bootstrap. So these are actually based on basically this following papers by all authored by Penatonians and collaborators. So let me just give the number. 665. So this is the basic setup is there. Of course, there are one more example. I don't know whether I'm going to cover it or not. So this is the main reference which first applied these whole ideas to 3+1 dimensional setup. But there was a paper by the same group of authors who did it also in two-dimensional quantum field, two-dimensional quantum field, like 1+1 dimensional. So that is this. This is 1 plus 1d, and this is explicitly 3 plus 1d. So I'm going to focus on this 3 plus 1d business, but in the 1 plus 1d, of course, a lot of, I mean, these kinds of bootstrap constraints can be solved analytically and to obtain various kinds of integrable models. And however, 1 plus 1d, at least in their work in 3 plus 1 dimensional work, 1 plus 1d has actually acted as an inspiration. Also, it has given some motivation to do stuffs in 3 plus 1 dimension, where this luxury of integrability, at least doing things exactly is not there. Okay, so we will set up this numerical problem. So just to begin with, what are the ingredients that went into this numerical problem? So I went to the next slide. So first, of course, is that went that means ST equal to T of TS. And of course, already the analyticity property that we have mentioned, that means that it is analytic. So what they assume is maximal analyticity. That means the scattering amplitude TST is analytic everywhere in the complex ST plane except possible bound state poles and the thresholds. And of course, the unitarity. Only the unitarity constraint is imposed in the numerical scheme in terms of partial wave unitarity, where these are partial wave coefficient of the whole S-matrix, where just to refresh the memory, S is equal to I plus T. I plus T, and this partial wave is coefficient, the explicit expression is given by this integral against the Legendre polynomial. Where X is the usual, X has the usual expression in terms of SNP. By the way, I must say X is this, and here L is only even. So L is even because we are considering only identical particles. Okay, so these are the ingredients that will go into and also there is this real analyticity, which basically tells you that T ST is equal to T S star T star. So these are the ingredients that will naturally go into this whole numerical explanation. The only difference from the analytics so far is that these guys have considered this maximal analyticity. That means what has been beyond what has been proved rigorously, but for the numerical explorations, and this has given some sensible results. So they believe that to be true. Okay, so the first point is that, so this is the starting ingredient. Let me go to the next slide. So the first thing is to come up with an ansatz. I mean, what we are looking for. I mean, what kind of, I mean, when you are trying to do some numerical exploration, we will essentially do stuff in this computer. So we need to tell computer what kind of variables we are trying to look for. That is why we need some ansatz. However, there's a problem, and the problem is this, that the analytic structure of TST, that is the scattering amplitude, has all these branch cuts in these planes. So somehow we have to take care of those branch cuts, or somehow we have to map the plane in such a fashion that those branch cuts are automatically taken care of. So to do so, we take help of a model problem. So to get some motivation.
Parthiv?
Yeah.
I think Karan has a question.
Yes.
Hi, sorry. Can you go back to the previous slide? I mean, are you restricting values of small t in this assumption, like t is less than or equal to 0 throughout, or something like that, or t can be anything?
No. Yes. So for example, here we are considering t to be, t is to be physical. So x will be always considered to be between -1 and +1. And for sorry, I should just so I'm considering this m equals to 1 here. So for x equals to -1 and +1, and for s greater than 4, so that will accordingly fix the value of t. So it will be negative, but the exact value will be fixed by that.
It can be 0 as well, right? So basically t less than or equal to 0.
Yes. Yeah. Right.
Okay. Just wanted a clarification. Yeah, thanks.
Yeah,
so in the case where you want to consider t greater than 0, I mean, does this get modified?
Okay. So that is an so for s greater than 4, that's an unphysical domain. So I don't know. I mean, what at least numerically, what will be the point? I mean, yeah, that's the point.
Okay, thanks. Yeah.
Parthiv, can you give the relation between this SL and AL, because earlier you expanded the T to be in terms of AL?
Okay. Yes. Okay. Exactly. So recall this this integral. So let me just. So this integral -1 + 1 dx PLX PSX. This was actually L by S. This was 32 pi.
Thank you.
So SLS is essentially so let me just very compact. So SL is this. So the unitarity will be imposed in terms of SLS. So the total, I mean, even considering the forward snapping. I mean, I do not know why they did not do it in terms of ALS, just ALS. There is no clear cut, indication that why they.
Parthiv, follow up with Karan's question. So here, what did you say that T is restricted to be in the negative region? Is that right?
Yes, I mean, so S is the, so we are considering S to be physical, that means it's greater than 4.
Right.
And then we are considering X to be, so X is the physical, so it's a cos theta. So we are considering that to be between -1 and +1. That's the physical X. And T is determined accordingly. So T will be, for example, less than negative. So for the physical T is actually less than negative.
Right. Yeah, that I understand. I'm just asking, so in this positive geometry construction, so there also we hold one of the Mandelstam variables to be negative, right? Because we have the constraint, say S plus T plus U is equal to -4m square. And then here I'm looking at say 2-to-2 scattering or 4-point scattering. So there, we set one of the Mandelstam variables to take a negative such that S plus say U is equal to a positive region. I mean, has that, is there any connection between this T and in the positive geometry approach?
Okay. So I mean, of course, this connection has not been explored in this paper, but I think there may be. I mean, ultimately, at least this this suspicion is from this recent connection between positive geometry and conformal bootstrap. So there may be a connection. Only that connection is not explored. It's just okay.
Sorry.
Yeah.
Yeah, in relation to Arnab's question, so the 2-to-2 scattering there in the positive geometry, that was a tree level scattering, right? So the one particle, it was just a one particle being exchanged. Here, I thought you were considering Z2 symmetry so that you don't have one particle or three particle states, right?
Yeah, yes. Well, actually, so whatever I told, so in this numerical setup, they are not really considering this Z2 symmetry. It was in that analytic exploration, those guys considered the Z2 symmetry, but I think even that analytic explorations can be considered for without Z2 symmetry. But the numerical expression is completely general. So I think that one particle kind of stuff can also be taken care of.
Oh, I see. And just one more question. So I probably missed this. How is unitarity? How does the unitarity imply mod S if L is less than 1?
Okay. So you have to start with that mod of S plus. Okay, you have to start with. So I did not derive. I mean, show the result. I mean, not show you the entire algebra, but you have to start from this S dagger S equal to 1, and then you have to, of course, project this S properly into this partial wave basis. So it is that when you will do this, you will get this thing 1. That procedure is a little bit not straightforward, but it's after some algebra we'll get it. So maybe I will put that algebra in the notes or whatever the final notes will have.
Okay. Thanks.
Yeah. Okay. So we have to take we have to take care of. So we have to understand how to numerically how should we be implementing this function properly, because the main issue is that, of course, we have to make sense of this branch cut structure. So to make sense of this branch cut structure somehow. So one of the idea that these people actually
one more. Sorry. Here we are still dealing with theories with the mass cap, right?
Yes, mass cap. Yes.
Okay.
Yeah, that's mass cap. So one way these guys did it is basically they mapped to a disk. So what is that meaning is this, that so we have, let's look at the structure in the complex S plane. So let's say we have a bound state somewhere, but we also have a threshold, and we have a branch cut, of course, to this portion. So if we just remove the branch cut, so there are and so the idea of maximum analyticity is this, that the function Ts, so the function in the complex S plane the function Ts. So for the time being, let's consider let's just look at let's consider Ts T as just a function of one variable for the time being. Let's assume that T is some real. So S, you are looking at S complex. So the idea is that the maximum necessity principle tells you that this Ts is, so this is the complex, S is complex. Ts is analytic in this white region, so entire white region, of course, apart from this bound state poles, if any, and this cut has been, this branch cut has been cut out. So what these guys did, they mapped this plane to a disk, and the disk is like that. So let me just write down this. This is, say, S equal to some MB square, equal to 4. This is equal to infinity, and they mapped it to some disk.
Sorry, I'm a bit confused with the units.
Yeah.
So S equal to
Oh.
MB.
So MB square is MB square is the mass of the, so MB is the mass of the bound state pole. So bound state particle, let's say, if there is any. So I have not mentioned it, so it should be number. So everything will be measured in the unit of the mass of the like particle we are scattering. So here we have put that mass of the external particle m equals to 1. So suppose MB is, let's say, 0.5 m. So then actual MB will be ultimately taken by like 0.5, just 0.5. So
okay, thanks.
Okay, so this can be mapped to a structure like this. So just to understand where this thing is, everything is going. And so this was S plane, and you introduce a change of variable, a mapping rho S between this S plane and this is a unit disk. So this corresponds to rho infinity. This corresponds to rho F, and this corresponds to rho MB square. So the point of this is this mapping is that, so I'm going to write down the mapping in a while, but the point of this mapping is that now this, within this unit disk, so this is my unit disk. So as long as rho is within this unit disk, sorry. So so the TST is a holomorphic in this, inside this unit disk by apart from any bound states. So the numerical implementation is actually done in terms of these rho variables rather than this S variables, because in rho variables you can freely choose according to, I mean, you can freely choose your variables numerically from this unit disk structure. Other than because if it would have been it would have been directly from this S complex plane, then you have to take into account of this branch cut structure and so on and so forth. So here in this mapping, what happens? this branch point, this branch cut, this cut region is actually outside the, it's pushed outside the unit disk. And this lower half plane is mapped in this way, and this upper half plane is mapped to this upper part. And just to mention, so this is an like open Riemann surface kind of stuff. It also goes by the name of Stein manifold. So the numerical bootstrap will be done with respect to this rho variable. Yeah.
Yeah, I missed this mapping. So the upper half plane that is marked with orange, so that is being mapped to which region?
Yes, so the upper half plane is mapped to, so just think of this thing as a kind of so okay. So let me actually show you what really, because there's a it's almost like a so it's almost like you are somehow gluing the whole stuff. So it's not, sorry, I was actually wrong to say that upper half plane is mapped. So what you are trying to do, what this maps does is that this orange boundary and this green boundary, so it's just get pushed to some edges, and in doing so, the rest of this infinite extent of this plane, they are actually kind of glued together into forming into forming a compactness. So just to show you the explicit gluing, how that thing happens, let me just show how it's it's done. Let's suppose consider this 2 points on this plane, these 2 points. So these 2 points are actually kind of deformed to so that's how they are mapped basically. So this is how they're actually. So that's how these two are. This mapping happens. So in a sense, it's actually some kind of wrapping up of this surfaces happening. So that's how you do it. So that you can think of that you are pulling out that cut region. So that cut region, meaning the small white strip of between that orange line and the green line. You're pulling that outside. In doing so, you are kind of distorting, and you are kind of distorting that whole stuff into stashing into a disk structure. So this is some kind of a Riemann surface. They call it a Stein manifold. So is the geometrically the mapping? I mean, does it make sense? You know?
Yes, I can slightly understand. Yeah.
Can you also can you give the row of S form?
Yes.
It would be easy
right. Yeah.
Okay. What is the center of the circle?
Oh, okay. So the center, center is actually it's so rho equal to 0 will correspond to it will correspond to a crossing symmetric point, like the way we are going to choose, so that will correspond to rho equal to 0. So let me give you the mapping explicitly, because otherwise it's a problematic stuff. So I'm going to the next slide.
I think Karan has a question.
Yeah.
Yeah, I have quite a few actually. So, okay, so you've got your S is equal to 4. Isn't there a cut even for S is equal to -4?
No. Okay. So
by crossing symmetry.
Yeah. Remember, but by crossing symmetry, you so S equals to -4. That cut is actually corresponding to U channel. So
yes,
what we are trying to do here is just to focus on S channel. But why we are going to do is I'm just coming to that point, that we are going to actually independently see all the 3 channels. And introduce a redundancy kind of stuff. But that is why we will individually look into each of these STU. So yeah, that's why we have ignored that minus stuff. That minus part.
Okay, but that should still be incorporated in this picture in some way, right? Because you want to still satisfy the constraint of S plus T plus U is equal to -4. So
yes,
I mean,
yes,
how is
yes,
that being
yes,
satisfied here?
we will. So yes,
okay,
right.
And
so
then the second question. I mean, okay,
yeah.
Please, yeah.
Yeah,
you
so
will mention that in the next slide.
Yeah. So that constraint that we're talking about, that will be a very so that will be the key point of this analysis, and I'm coming to that. Yeah.
Okay, and the next question is this I epsilon prescription. So I mean, as far as I understood it, there is this T of S plus I epsilon from the top is equivalent to P star of S minus I epsilon from the bottom. So how is that I epsilon prescription? Basically, you could go from the top, wrap around, and go to the bottom. So is that reflected in some kind of antipodal matching from the Stein manifold or something like that, or is there?
So yes, you have told me right, but I think so that point they did not clear up. But I guess that's what they're trying to do. I mean, they're trying to somehow. So I think it will be that if you just so what is the meaning of so for example, when in the S plane you are when you're approaching that orange line from the above, so that will be equivalent to like approaching that orange boundary towards like the northern hemisphere kind of part. And similarly, the other thing, like for example, T of I minus I, so that will be like approaching. And I think the relationship is that as you go towards those boundaries, those should be related by that what I just told. Yeah. So that means
so your boundary is your T physical line, is it? That boundary on the top is basically your T physical.
Yes. Yeah.
Okay, thank you.
Yeah. Okay. So let me write down the mapping. So the mapping is this. S and S equal to S naught 1 minus S square S 16 S and plus S whole square. So this is the mapping. Yeah. So this is the mapping that that maps this S to rho S. So rho S is actually equal to this that rho variable. So S naught is chosen to be 4/3, so that such that rho S equal to 0 at S equal to 4/3, which in this case is the crossing symmetric point. So this I told you to illustrate what is happening for a single single S variable. But what is done to do the numerics is this, that the crossing symmetry is applied in a bizarre way. It's not directly. So they elevate the scattering amplitude to a function of 3 variables. So really recall that S plus T plus U equal to 4. This is the on-shellness condition. But for the time being, they just let this redundancy to step in, that there's this S. So as if T is an independent variable, T is a function of 3 independent variables. Then they make this change of variable by the same policy. And in doing so, they live in what is called, is basically a 3 disk. So what they satisfy this. So at this stage, whatever manipulation we are doing at this stage, this on-shell constraint, that means S plus T plus U equals to 4, that's been ignored. We are just thinking that the scattering amplitude T is a function of 3 independent variables, and we are doing this variable change to this rho S, rho T, rho U, so that now we are. So remember, by maximal analyticity, T has poles, of course, corresponding to bound poles in each 3 channels, and also they have the threshold cuts corresponding to each channels. For the time being, we are assuming that all these thresholds are independent, and we are basically mapping that C3. So mapping that C3 plane, because we are 3 variable, to this delta, delta 3, or what they call this to be a 3 disk, such that within the 3 disks, the rho S, rho T, and rho U satisfy this constraint. Now we come to the now we are going to take an ansatz of for this TSTU in terms of rho ST, rho S, rho T, and rho U, which satisfy the analytic constraints, the analytic requirements of the maximal analyticity property. What does it mean is this.
I think Parthiv, I think Karan has a question.
Yeah, I'm sorry, I'm a little naive about all these things, but okay. So I'm familiar with like this Mandelstam plot of STU. So you're saying that this delta cubed or triangle cubed is basically that region in the Mandelstam plane where not the S greater than M4, not the T greater than 4, not the U greater than 4, but that triangular region is what you're focusing on?
No. So let me go to the previous slide and show you what I'm trying to do. So in this slide, I have I have just I have mapped this S plane to this one single disk kind of stuff. Okay, but that was when I was just considered that TST. I mean, for example, TS as just a function of single complex variable S. Now think that. Now you go to the full-blown kind of structure. We say that okay, T is a function of 3 complex variables S, T, and U. Then my I already mentioned in that maximal analyticity that this function T as a function of the 3 complex variables STU will have poles corresponding to bound states in all the 3 channels, and it will have this threshold cuts or the threshold points in all the 3 channels. So essentially, if I just to say so if I want to visualize T on this as a function of these three complex variables STU, so you can think of there are 3 copies of this kind of plane. So one for S, one for T, and one for U. And you are doing this map row to each of the copy to take it. So to take that each copy to a disk, and ultimately what you are getting is that you are starting with this T as a function of this topological product of 3 copies of this kind of complex plane, and you have mapped that to a function of to a function T, which is defined on a topological product of these three copies of this kind of disk. So that is what you have done. So it is this entire plane has been mapped to this this region, but it is done with respect to S and T, S, T, and U all assumed to be complex. We have still not put that yet. So does this answer?
Partly, but not fully. So I get the Mandelstam plane is real. I'm not literally saying the Mandelstam plane. I'm saying the complex generalization of that Mandelstam plane with the with that triangle in the middle, which would cover all bound states. So that triangle in the middle would cover the bound states, if I'm not mistaken. Am I right? So you draw like this ST axis, and then there'll be a straight line or whatever, as far as I know. And you're confining yourself to the complex generalization of that triangle in the middle. Is that correct?
No,
or it's
not just triangle, but also okay. Let me just draw one second.
And short follow up. I mean, because I won't take any more of your time. So I mean, that last line that you have where rho S is less than 1, rho T is less than 1, and rho U is less than 1. I would have assumed that.
Sorry.
Karan, you are not audible.
Case, how do I ensure that?
Karan, we couldn't hear you for last 1 minute.
Oh, sorry. Can you hear me now?
Yes.
So which part didn't you hear? So I mean, So the Mandelstam question was clear, I hope.
Anything you said after, you don't have much time, and
I don't have much time. Okay, So this last line that you have on rho S less than 1, rho T less than 1, and rho U less than 1. I would have thought that some combination of them would have to be bounded in order to satisfy S plus 2E plus U is equal to 4. But you're saying that I can independently look at S, T, and U and close my eyes and everything should be fine. And I don't see how that is sort of resolved.
So you are absolutely right, because the point is that in this formalism, what they do, they impose this S plus T plus U equals to 4 this combination in a in a different way. So ultimately, this constraint has to be put because this is absolutely required. But for the time being, they're just closing. They're just closing their eyes to this constraint and proceeding, and they will have some kind of ansatz. They will introduce some kind of ansatz, and on that ansatz, they're going to put this S plus T plus U equals to 4 constraint, and that will have an important consequence, actually, some structural change in the ansatz. So I guess if you properly analytically express in those terms, you can find out these regions that you are asking, that is some kind of combined regions. But this region is actually resulting in, because I'm looking at STUs as independent of one another, just shutting my eyes to this constraint for the time.
Okay, so very, very, very fast question. So you're saying that you're going to take this to be like this in the beginning, but then numerically you're going to sort of determine the correct bounds. Is that what you're heading at?
Even even before, for example, implementing the actual numerical. So I will write shortly an ansatz, and on that ansatz I will put this constraint, all this constraint into this thing. I personally think it's too fascinated the numerical computation, that the style they have taken up. I mean, that's how they do it. It could have been, it can be done in better ways, but yeah, I'm just describing what has been done.
Parthiv, continue.
Okay. Okay. So, having this, having this kind of stuff. So, what they are really doing, they are so this is known as something analytic extension. So basically, due to this on-shell constraint, that means s plus t plus u equals to 4, this TSTU is actually a function of, so I'm in slide 69. It's actually a function of two variables, but in treating u as an independent variable, we have analytically extended this TST to a function on this delta 3 kind of domain, and that this can be done, that this thing can be done is guaranteed by a mathematical theorem which they mention in the paper, which they call Cartan's theorem B, of course, whose content I do not understand, but it's some kind of theorem which tells us that this can be done. So the point of that, we do not need to know that theorem, but it's that theorem ensures that the kind of stuff that we are doing is a valid and a legal thing to do. In doing these things, we will not going to introduce any more singularities, any more singular structures that is already there from the TST analyticity properties. Okay, so then let me go to the next slide and write down. So now we are going to write down an ansatz for TSTU. In terms of course, so let me just to signify that I'm using du. So see these first three terms are actually for bound states. You may be surprising that why they have introduced STU to write down the bound states instead of rho s or rho t or rho u. And I think it's just too easy to express that in terms of STU variable. However, the other part, and this is very important. This part they are expressing in terms of rho STU, rho s, rho t, and rho u. And see, this is a power series, and it's power series, and this function is an analytic function in rho s and rho t and rho u. And that they are assuming this kind of an ansatz. They are taking it from the analytic structure. Recall when we did make this from S to rho s and T to rho t, U to rho u transformations, we basically pushed all these branch cut structures to the boundary. So inside this kind of that polydisk I told you, that delta to the power 3, within that, this rate square, this quantity within the rate square is actually analytic. So this is the ansatz that we will do the numerical stuff and numerical computation. So that has been subjected to the numerics in as far as we go. So here, but there are two things still missing. We have not still incorporated the crossing symmetry. Number one, And number two is that we have still not incorporated, we have to incorporate that S plus T plus U equals to 4. That means that on-shellness condition, on-shellness constraint into this ansatz. So,
Parthiv,
yeah.
Can you tell me why in the red box thing you have written down in a power series expansion?
Oh, okay. So this is something that this is again a theorem. This is this is a mathematical theorem that if you have a function which is holomorphic apart from a which is a function which is holomorphic in this kind of structure, then you can write down a Taylor series expansion. So this looks like a Taylor series kind of expansion, which will converge within that disk. So this is some mathematical theorem they are mentioning, from which they are writing. So this is just the mathematical theorem I told you, this Cartan's theorem B. It is this theorem that is enabling them to write down this guy within red square as a power series expansion.
And do you expect that, because like this map between rho S and SA is basically in terms of square roots, so do you expect that always the non-analytic structure beyond S greater than 4 region, the threshold region will be always kind of a square root branch cut kind of thing, only then you can write it down?
Yes. So actually, I think this is this I've not seen any clear indication, but this recent some of the papers have wrote, but I think it's a consensus that this square root kind of branch appears always in even dimensional theories. That is what they use. So I think that is what they use. Even in, I think, in two-dimensional theories, because this ansatz that this transformations, they got this motivation for transformation in studying in two-dimensional theories, and also in fourth dimension also, and that can be seen from the unitarity constraint that I wrote the other day. From that factor, you can actually see that it's always square root kind of stuff in fourth dimension. Okay. So first thing is we have to incorporate this crossing. Crossing simply tells you that, what are the parameters in this ansatz? What are the parameters that we are going to, so in usual this kind of numerical bootstrap work, people put bounds on parameters of the theory. What are the parameters that ultimately we are interested in? So we are interested in these parameters. This rho ABC and this G squares, where we will assume some knowledge, some property about the spectrum. So remember this MB spectrum, this MB will be a property of spectrum. And of course that force stuff or the threshold structure, these are also part of the spectrum. So the parameters that we are going to ultimately investigate is this G squared and alpha ABC. So we will try to see ultimately what this crossing has to do, how the crossing manifests itself. So first thing is that crossing manifests itself into that this guy is totally symmetric. Is totally symmetric under ABC interchange. This is very straightforward to see. So just to illustration, this you have alpha ABC, rho S A, rho T B, rho U C, but then suppose you demand by crossing is going to TST crossing. You demand ST crossing should give you this constraint. Then this should tell you. And similarly, if you check for other crossing conditions like S going to T or T going to STU, you will always find out. So that is the first thing, that alpha ABC is totally symmetric. So from now on, we can actually group not just we'll consider this, but we can group them together, which is nothing but so we will introduce, we will now express everything in, will be told in terms of this rho ABC, which is basically this permutation terms.
Parthiv, one quick question.
Yeah.
So you are taking G square as the coefficient for all the three channels. There itself you are assuming some kind of crossing, right? ST and
Yes. Yeah. So I would say that that part we I think this is I just So in that bound state part they have already considered this crossing, but in writing these ansatz a priori they did not consider any crossing, and they are just implementing the crossing here actually. Yes, you're right. Okay. So the consequence of crossing is pretty straightforward. Now let me go to that next constraint. So let me go to the next slide. So now we are left with ST plus U equal to 4. We have to implement this. If we express this ST plus U equals to 4 in terms of this rho ST, rho S, rho T, rho U variables, we find out this constraint becomes zero. So this is the constraint that gets translated from ST plus U to these rho variables. Now, this constraint of what they call as of order 5, what does it really means? That order of a term. So let me just write down what I mean. A plus B plus C, and maximal order, because this is like a polynomial constraint essentially in row variables. So the maximal order is what we will call order of the constraint. So clearly, order of this constraint is 5. Now, what does it tell you? Yeah.
I'm very sorry. My internet completely blacked out and came back on, and your voice was also gone before that. Can you just tell me how you got this red box equation?
Oh,
I mean,
so
I totally missed it.
Yes. So what you have to do this, you have to put this S plus T plus U. You have to represent them in terms of rho S and rho T and rho U, and then you have to do some algebraic manipulation to get this thing. So I think it's a lengthy algebra by which you will get this. So it's just a straightforward algebraic manipulation from that.
Okay, I think I wanted that. I wanted to see a permutation notation. 1 second.
Okay. So it's in the previous slide.
Yeah, that's
this is the permutation. Okay. So, right. So this is a constant 5. So let's just see what does it really mean. No, you can remove. So it is better to using this constraint. What you can do is that you can express this rho 1 to 2 in terms of this lower order terms. So what I tried to say is that this you can write down this constraint. So use this constraint. Other lower order terms. So what will the consequence of this on the analytic structure of this ansatz? So if we go to the next slide. So remember this structure was so alpha A B C, and since it is completely symmetric, I can club them in this fashion. I can always choose this kind of ordering. Now, just look at a particular, let's say n equal at particular n. If n is, so just write down. Okay. Theta. If n is less than 5, I mean, we can just prefer to say that if n is less than 5, we choose not. I mean, you can say here that okay, I can. So I'm in the previous slide just to illustrate. So, for example, I can say that okay, I can choose this, let's say rho 1 0 0 to express everything in terms of the rest of the thing. But you know that will somehow that grouping will be a little bit problematic. So we can group in a particular way. We say that we are going to express the highest order stuff in terms of the lower order, highest order term in terms of the lower order terms. If we decide on that kind of grouping, then as long as n less than 5, and as long as n less than 5, so I'm in the next slide, slide 72. If n less than 5, I cannot really consider, I have to consider all the terms. Then there is no elimination. Elimination in the sense that in what sense we are doing the elimination. So what we told that rho 211, so let me just go back to the previous slide. So rho 122, so I'm expressing rho 122 in terms of rho 112 and this lower order terms like rho 120, rho 11, and rho 100, and so on and so forth. So equivalently, what we can just say that, you know, if this is the constraint, then there is no point of keeping that rho 122 term separately in the ansatz to begin with. So we are going to put the alpha 122 equal to 0. So it is in this sense, this s plus t plus u equals to 4 constraint will lead to elimination of many of those variables. Elimination in the sense that many of those variables, those parameters will be straight off to 0 to leave us with some finite number of variables. So let me show it to a little bit more explicitly.
You mean you'll set the alpha corresponding to that?
Yes, alpha corresponding to that rho to 0. So for example, using this constraint directly, what I will do, then for if n less than 5, there's no elimination. we just saw n equal to 5. We chose to 2, 1, 1 equal to 0. Now we can, now that is one constraint. You may be thinking that, okay, that it's one constraint, it's done. But if I multiply that constraint by a symmetric monomial, a lower order symmetric monomial, I can generate new constraints. I mean, symmetric monomials which are actually not a priori 0. So what kind of, sorry, but I did wrong. Other kind of symmetric monomials, I can create new constraints. So what I try to say, that suppose you multiply that constraint with the monomial rho 1, 0, 0. Then this will generate a new constraint. It'll be a higher order constraint rather. So write down the explicit expression. So it is, they will generate this a higher order expression like this. So why I'm saying higher order? Because now you see, now there are two terms which are, I mean, the maximal terms are two terms. One is 2, 2, 2 and one is 1, 2, 3. So now what you can do, now you can eliminate another, term using this constraint in the sixth order stuff. And you can follow a certain order or certain grouping behavior to say that, okay, I'm going to eliminate this coefficient of this row 1, 2, 3 terms in terms of the rest of the thing. Or perhaps you can also limit like row 2, 2, 2 terms because it's starting from 2, 2, 2. I mean, it's just some grouping scheme you want to follow. Let's say the last term, you're going to strike off that coefficient. So what we are going to do, that suppose you will be looking at a certain order or order term in that expansion, and you just using this ST, this S plus T plus U equals to 4 constraint manifests itself into this kind of higher and higher, will result into higher and higher order constraint. And at each order term, I can strike off a finite number of these parameters alpha, and I will be left with, I will be left with a finite number of parameters, a smaller number of parameters, not that large. So in this way, the S plus T plus U equals to 4 constraint will manifest in elimination of some terms from this sum. Okay, so before I go ahead, if any question is there.
So how did you generate these higher order terms? Can you explain once more?
Oh, okay. So what I did, I basically multiplied the previous constraint. So the constraint in the previous slide, this one that we got directly, with
this one or the previous one?
Yeah, the 71, slide 71.
Okay.
So this constraint within this red box by, let's say, row 1, 0, 0. That's one symmetric monomial. So I basically multiplied it with that constraint to get this new constraint. And this will be an independent constraint, by the way, because it's actually changing the entire polynomial order. So it's basically like by multiplying, you're multiplying by one variable.
And what is the objective here? Like solve the lower order in terms of the higher order?
Objective is this, that because next time we're going to put this into computer, and before putting into computer, you would like to have, because by construction the ansatz that we have taken is actually redundant ansatz, because it's really not taking care of that S plus T plus U equals to 4 constraint. but that you have to put because that is the on-shellness constraint. So before you put it into a computer, you should be able to, you have to try to see that what is that what is the effect of that on-shellness constraint on this ansatz. And so the point is that before taking the final step, you simplify as much as possible and then put it on the computer. But this task is also done by computer. But what I'm trying to say is that the final program before putting into the final program.
Okay.
So for computational purpose, of course, we do not consider, for example, so this is formally it's an analytically or formally it's an infinite sum over ABC. But when you put it in a computer, it's definitely not we are not going to work with an infinite sum. So what people do is they truncate this sum. Let's truncate this sum by okay, I'll go to the next slide. So the ABC sum is truncated by A plus B plus C less than equals to some n max. And this n max will be given a numerical input. So we basically truncate the sum. Of course, good question is that, for better result, you would like to take sufficiently high value of n max because ultimately that should simulate. But once we will see, I mean, what these people did in their original paper, they took n max equals to 20. And that was quite strong. Even taking n max equal to 20, of course, it's a heavily computational task. But even taking n max equals to 20 gave them quite good results. But once you take this n max equals to 20, then of course so you're considering up to A plus B plus C equals to n max, and you will be, of course, will be interested only up to constraints of the order n max. So first so the algorithm is this, that so an algo looks like this. First, truncate the ABC sum to n max. Second, eliminate alpha ABC variables according to the S plus T plus U equals to 4 constraint. So that finally you are left with a finite number of variables, which is G square and alpha ABC, where of course you have now alpha ABC, not only A plus B plus C is n max, but also you have taken care of this elimination. So this is the ultimate variable. This is the ultimate parameter. So this will be the parameter space. And it is much, so for example, even if you take, let's for example, n max equal to 20, there are a huge number of alpha ABC parameters to start with. But after you do this elimination, properly, systematically, you actually reduce the number of variables by quite a much. So that gives you a computational mileage. And it is this computational mileage which is actually required, because anyway, it's very computationally taxing. So what we so far considered? So far, we had taken into account the analytic structure and exploited the analytic structure to go to some suitable variables. Next, we had taken care of the crossing symmetry. Finally, we have also taken care of the S plus T plus U equals to 4, that is the on-shellness condition. Now, the final bit of the problem is the unitarity. That we have not still taken care of. So that is the final part. So let me just describe the unitarity and how to take care of the unitarity. Okay. So let me go to the next slide.
Parthiv?
Yeah.
Before that, can you remind me what was G square?
Oh, G square was the so residue was the residue of the bound state pole. So it is in slide number 70. So G square is the residue of the bound state.
I see. Okay.
Okay. So,
and here this n max that you write it down, that corresponds to what? The order of the row that you were considering earlier?
Yes. So for example, let me go to the ansatz once again in the previous slide, meaning slide number 72. So so it is row ABC has a power. I mean, it's a total power like A plus B plus C. So it is that power we are restricting, that A plus B plus C less than equals to n max, some cutoff.
And does it have any relation with the, I mean, earlier assumption or earlier the goal of finding this for large spin? That
No, it's not. It's I think it's like, you know, whenever you are trying to do a any kind of infinite series in numerically computed, you have to somehow truncate that sum, truncate any infinite sum into somewhere, then try to see what happens. I think it is that kind of truncation. However, you know, one can question that whether putting even more variable will more terms will be give any newer mileage or something. So these authors, they demand that they have experimented. Of course, they have very strong computational facility, that the brute force going to some higher end really does not change the physics conclusions. Okay. So
Parthiv?
Yeah.
What kind of setup is this numerics being carried out in? I mean, what is the programming in which it is implemented?
Oh, okay. So this part, what I'm going to tell, I mean, so far what I've been telling you, these are all Mathematica, these are done in Mathematica. But so all these things, what the next part I'm going to tell is this unitarity. This unitarity is actually, that constraint is dealt with what is called a semi-definite program, and especially the semi-definite programming in Bootstrap. So that was written, that is, I think that is written in C. That's an open source software, by the way, but that is written in C++, I guess. So that is where, that is what gives the final answers, and that is run in cluster system.
Okay, thanks.
Okay, so let me just go to the unitarity. So now we need to take care of the unitarity constraint. So recall my unitarity, my unitarity constraint was SLS less than equal to 1. Well, so this is essentially, now if you want to check, so remember in SLS, in determining SLS, we will need the ansatz of the, we have to, because SLS we have to determine the ansatz of TL, the ansatz of T that we have considered. But there are, first of all, infinite number of values of S, if you think in terms of analytically, and also infinite number of L. So what numerically is done, this S is chosen, or it's really not, this S is chosen from a grid of values of S. It's taken, and more or less it's taken a uniform distribution, kind of uniformly they are taken. And L, people, they also check this unitarity for, I mean, not for all L. Well, that's not just possible. They check this unitarity up to some L max, where L max is at least what they find out that for getting sensible results, L max is at least greater so one should write down that L max is greater than or equals to N max. So this is there is no I mean analytic reason or numerical analysis kind of argument that why this is so. They had just by brute force experimentation they have found out that L max has to be at least as large as N max. Has to be at least as large as N max. So for example, they considered in their paper N max equals to 20, and they also considered up to N max equal to 20 or slightly above to 20. And it's there they saw that when L max is at least is bigger than N max. Of course, if you make too big, it was really not making any difference. But if it's smaller than N max, so smaller than N max, it was not not giving much, not very believable result, a trustworthy result. So this is a completely their experimental observation. I mean, there is no concrete reason for why it was. Yeah, go ahead. Yes.
Yeah, no. So this SL. So here this L stands for the spin, right? I mean the spin that you were talking about earlier in terms of this. Partial wave expansion. Right. So doesn't it also imply that this formulae or this analysis is valid for large spin in that way? Because as you were mentioning that L less than N, I mean, it's not very, it's not giving much correct result.
But of course. I mean, well, the question is that what I will say large L is a good question. I mean, even so, for example, the other day the analytics I was talking about, it was like some asymptotically large L or something. But this is large L, but it's still some kind of finite L. So even to make any connection of that to this, you have to somehow resum that 1 by L expansion so that you can put some L equals to finite value here. Here L is large, but it's not that large kind of stuff. Yeah, I would say. Okay, so once again I reiterate that this is their observation that, and also this recent observation of 3 of my collaborators that who have implemented these programs, that this is like L max has to be as large as N max at least to go, at least whatever the experimentation they have done. I mean, it would be best if one can do a concrete numerical analysis. I mean, the analysis of the numerics to understand why this is giving the good result. So,
Parthiv,
okay.
Parthiv, what do you mean by, so if you take L max to be less than N max, you said you get some wrong results. What do you mean by wrong results? Like, what does it mean? Hello?
Okay. So I will. Yeah, actually, I have to show it you in terms of some. Yeah. Hello.
Yeah.
Am I audible?
Yeah.
Am I audible?
Yes, you're audible.
Oh my God! Just a second.
Parthiv, you're audible, but I think there is a lag.
So. Okay. So what I'm trying to say is this, that I see. Oh, okay.
Parthiv, are you there?
I guess he has left.
Yeah, let's wait for him to join.
Hello?
I think we are all here, but Parthiv is not.
Yeah. Can you pause the recording?
No, it's only 5 minutes left.
Okay.
But people can discuss other things if they want. Manu, you can ask your question to Biswajit.
I was not there for last 10 minutes because the internet is very fluctuating in HRI. I am not even able to understand what is going on.
Biswajit, we don't believe you.
Okay, he's writing something.
Yeah. Okay.
Yeah, please resume.
Yeah. So the question was that what kind of problems? So I think one problem was that there was there is the question of numerical stabilization that does not happen in the case of when you take Lmax smaller than Nmax. So yeah, I will come to this smaller details. Today its time is over almost, so maybe tomorrow. But just to write down the just to sorry, this network disruption. Okay, so the unitarity constraint, let me just write down quickly. It can be actually cast into when you have a grid of S values and also some finite number of L. It can be cast into a what is called a semi-definite problem. So just to set the stage, let me just write down how this can be set into a semi-definite problem. To do this, we can write down this TST
Parthiv, are you there?
Yeah, I'm there. So is it? I mean,
oh, okay.
So apparently this thing is not writing properly.
I think there is a internet lag issue, Parthiv.
Okay. Yes, I don't know.
Yeah.
Yeah, maybe. I don't know. Okay. Now I'm hearing people. I was not seeing. The writing is also not coming.
Do you want to disconnect and connect again?
Okay. Yeah, that's it.
Not yet, but I think, can you try writing? Now it is coming.
Okay, so is it coming instantly? Just okay.
Yeah, almost instantly.
Okay. So let me just maybe for some evening time and the network is creating problems. So let me just quickly just write down the setup. So yeah, so the way you do it is this: you write down you can write down it's what is known as a semi-definite programming. So let me just write down how it's set up. ST4 minus S minus T. This is written as two row matrices actually constructed, where this row matrix is actually the matrix of the parameters. So for example, G square, G square, G square, and then alpha 1, 0, 0, and so on. Where this amplitude matrix is the one with, let's say, minus S minus MB square. So basically, I have written it as a product of two. So two, like the usual row column vector multiplication way. And then let me just go to the next slide. Then I can write down very naturally this SLS as 1 plus I. The inner product of these two kind of matrix. Now, the constraint of this less than 1, this ultimately translates to do it carefully, so that they are all finite, they all involve finite matrices, which is where I is imaginary part of this matrix, and noise real part of and they can be rearranged that this condition, you know, that it is the ultimate, you know, this is the integrity conditions, and that this condition actually translate into a semi-definiteness of a matrix. If I construct a matrix M, then this condition translates to M being positive semi-definite. So this is positive semi-definite. So this unitarity constraint ultimately can be cast into a positive semi-definite condition for a matrix which is suitably constructed out of these quantities. So it is here that the semi-definite programming enters. So it is here that the semi-definite
So Parthiv, why did you choose this matrix M? What motivated
no,
you?
it's yes, it's basically we are going to use this semi-definite programming. You know, so I'm not going to describe it today because it's a long stuff. But the point is that this we have found out a matrix M, which is the unitarity condition can be cast into an equivalent statement of that M, that there exists a matrix which is semi-definite, positive semi-definite. Now we can actually exploit to use this semi-definite programming, so which is a kind of a convex optimization problem to obtain the kinds of bound that we are going to see in the next lecture. So it's actually, this is the point where this is the reason, this is the point where this semi-definite programming actually enters. And I also think that this is the point where connection with positive geometry can be made. Yeah, that is where I stop today.
Okay, let us unmute ourselves and thank Parthiv for this very nice lecture. If there are any pressing questions, please go ahead and ask.
So in the later part of the talk, I got a little confused. I mean, I didn't understand the things very well. So what is its connection with your previous part of the talk where you were talking about this numerical bootstrap analysis?
Yeah. Yes. So this is, so for example here, so far I've been considered, for example, other kind of constraints like I have considered all these things. In this part, so this is also a numerical program, and this is where we will enter. So the unitarity constraint, the numerical way, so the numerical program or the numerical algorithm to implement the unitarity is this semi-definite programming that I will describe tomorrow. So that is where it's going to be connected. So ultimately we are going to do an optimization problem, and we'll see that how the semi-definite programming enters into it. Yeah, I have actually kind of rushed here, but yeah, we'll start more slowly tomorrow.
Are you going to talk about your entanglement constraining paper?
Yes, yeah. I mean, I will actually try to, you know, maybe instead of going into plots, I will just tell some entanglements.
Okay, I think we can. Oh, go ahead.
So can you explain the first line of this slide? How you can write SLS in this form?
Oh, which one? So sorry. Oh, this one. Okay. Okay. So for example, I wrote this TST in the form of this eta plus eta dot TST.
Right.
And what you have to do when you determine this SL, remember that you actually take this integral of amplitude with respect to this Legendre polynomials. So in writing this FLS, what you do the similar thing. So basically, you take this Legendre integral of Legendre polynomial of each element or each component of this TST vector, and that's how you construct this FLS. So FLS function.
Yeah. Okay.
Yeah.
Okay, I think let us stop the recording here.